Hello and welcome. I'm glad you're here. Maybe you've had a long day. Maybe your mind is still turning over the details of conversations, tasks left unfinished, or thoughts that won't quite settle. That's okay. You're in the right place. Tonight we're going to take a journey through some of the most fascinating corners of science. Not to test you, not to demand your attention, but simply to let your mind wander through wonder, to let curiosity be a companion as you drift towards sleep. We'll explore facts that span from the smallest particles to the largest structures in the cosmos, from the ancient past to the cutting edge of discovery. Some will be simple and comforting. Others will bend your sense of what's possible. But all of them, I hope, will remind you that the universe is far stranger and more beautiful than we often remember in our daily lives. Before we begin, I'm curious. How was your day? Whatever it was, whether challenging or peaceful, I'd love to hear about it in the comments below. And if you enjoy these journeys into the quieter side of science, consider subscribing. It helps me keep creating these moments of calm exploration for you. Now let's begin. Let's start with something ancient, something sweet. Honey never spoils. Archaeologists have discovered pots of honey in Egyptian tombs, 3,000 years old, and found it still perfectly edible. You could, if you wanted, spread it on bread today. The same honey that sat in darkness beside pharaohs, that witnessed the rise and fall of dynasties, that knew a world we can barely imagine, remains unchanged, still golden, still sweet. But why? What makes honey immune to the relentless march of decay that claims nearly everything else? The answer lies in its nature. Honey is extraordinarily low in water content, and its pH is quite acidic. Together, these create an environment where bacteria simply cannot survive. There's nowhere for them to take hold, no foothold for decomposition. The bees, in their ancient wisdom, have created something nearly eternal. It's a small miracle, really. In a universe governed by entropy, where everything tends toward disorder, here is something that resists. Not forever, perhaps. Nothing is truly forever, but for longer than most empires last, longer than human memory. And it reminds us that nature has been perfecting preservation long before we learned to can, to freeze, to vacuum seal. Now consider yourself, your body, your hands perhaps, resting on the blanket, your chest rising and falling with breath. Every atom in your body is replaced approximately every 7 years. The calcium in your bones, the carbon in your cells, the oxygen you're breathing right now, all of it cycles through. You are, in a very real sense, not made of the same physical material you were made of 7 years ago. You've been entirely rebuilt, atom by atom, like a ship with every plank replaced. And yet, somehow, you remain you, the same continuity of consciousness, the same memories, the same person who remembers childhood, who recognizes their own face in the mirror, who carries forward through time with an unbroken sense of self. How is that possible? How can you be the same river when all the water has flowed away? Perhaps identity isn't about the stuff we're made of at all. Perhaps it's about the pattern, the arrangement, the way the atoms are organized and reorganized, maintaining a structure even as the substance changes. Like a whirlpool in a stream, always there, always recognizable, even though the water passing through it is never the same water twice. You are the pattern, not the particles. A beautiful, temporary arrangement of matter that knows itself, that persists across the constant flux of existence. Beneath your feet, if you're standing on soil, there's a conversation happening, a network you cannot see. Trees communicate with each other through an underground system of fungi called the Wood Wide Web. These fungal networks connect root to root, tree to tree, across entire forests. Through them, trees share nutrients. A mother tree, tall and established, will send carbon to her saplings through these threads, helping them survive in the shade of the forest floor, where sunlight barely reaches. When a tree is attacked by insects, it sends chemical distress signals through the network, warning its neighbors, who then begin producing defensive compounds before the threat arrives. It's cooperation on a scale we're only beginning to understand. The forest, which we might imagine as a collection of individuals competing for light and space, is actually more like a community, a collective, where the strong support the weak and information flows through invisible channels. The fungi act as intermediaries, receiving sugars from the trees in exchange for their networking services, creating a relationship that benefits everyone involved. Imagine that. Beneath every forest path, every quiet grove, there's this hidden internet of life, pulsing with messages, transferring resources, maintaining the health of the whole. The trees aren't alone. They never were. They're part of something larger, something that functions almost like a single organism spread across miles, connected in ways that make our own internet seem almost crude by comparison, and all of it happening in silence, in darkness, beneath our notice. Let's journey outward now, away from Earth, to something almost unimaginably dense. A neutron star is what remains after a massive star explodes in a supernova. The core collapses under its own gravity, compressing matter to densities that don't exist anywhere else in the universe except in black holes. And here's what that means in practical terms. A single teaspoon of neutron star material would weigh about 6 billion tons on Earth. 6 billion. That's more than Mount Everest, more than all the buildings in a major city. All of it in a teaspoon. How is such a thing even possible? In normal matter, atoms are mostly empty space. The nucleus at the center is tiny compared to the electron cloud surrounding it. But in a neutron star, gravity is so overwhelming that it crushes atoms together, eliminating all that empty space. The electrons are forced into the protons, creating neutrons, and those neutrons pack together so tightly that the entire star, which might be only 20 kilometers across, contains more mass than our sun. It's matter in a state we cannot recreate, cannot fully understand, can barely imagine. If you could somehow bring a piece of neutron star to Earth, it would instantly fall through whatever container you put it in, through the floor, through the ground, plummeting toward the center of the planet under its own impossible weight. Reality, at its extremes, becomes stranger than any fiction we could devise. And neutron stars are out there, spinning in the darkness, remnants of stellar death, holding together against all odds. Back to Earth, to the ocean, where something extraordinary swims through the darkness. The octopus has 3 hearts. 3. 2 of them pump blood to the gills, oxygenating it, while the third pumps it to the rest of the body. But here's the strange part. When an octopus swims, the heart that serves the body actually stops beating. This is why octopuses prefer to crawl along the seafloor rather than swim. Swimming literally exhausts their main heart. And that's not all. An octopus has 9 brains. One central brain, yes, but also a smaller brain in each of its 8 arms. These arm brains can act independently, solving problems, manipulating objects, even tasting things without input from the central brain. An octopus arm, severed from the body, will continue trying to bring food to where the mouth used to be. The arm itself knows what it's doing. It has agency. Oh, and their blood is blue. Not metaphorically, literally blue, because it uses copper-based hemocyanin to carry oxygen instead of the iron-based hemoglobin we use. In cold, low-oxygen environments, copper is actually more efficient than iron, giving octopuses an advantage in the deep sea. These creatures are so different from us, so alien in their biology, that encountering one feels almost like meeting an intelligence from another world. They evolved complex nervous systems completely independently from vertebrates, taking a different path to cognition, to problem-solving, to awareness. And when you watch an octopus navigate a maze or open a jar or change its color and texture to match its surroundings, you're witnessing a kind of intelligence that emerged from a completely different evolutionary branch. We're separated from them by over 500 million years, yet here we both are, thinking, problem-solving creatures sharing the same planet. There's a point, a very specific point, where water becomes all 3 of itself at once. It's called the triple point, and it occurs at exactly the right combination of temperature and pressure, where ice, liquid water, and water vapor all exist in perfect equilibrium. Not transitioning from one to another, but being all 3 simultaneously. Solid, liquid, and gas together in the same space at the same time. For water, this happens at 0.01 degrees Celsius and a pressure of about 611.657 pascals, roughly 0.6% of normal atmospheric pressure. It's a razor's edge of conditions, a single point in the vast landscape of possible temperatures and pressures where this balance can exist. Stray even slightly in any direction, and one state dominates, the equilibrium breaks. But at that exact point, you can watch water boil and freeze simultaneously. You can see ice forming even as bubbles of vapor rise through liquid. It's as if water can't decide what it wants to be, so it becomes everything at once. A physical indecision, a moment of perfect possibility before conditions force it to choose. It's beautiful in a way, a reminder that the states of matter we take for granted, solid, liquid, gas, are just different expressions of the same substance under different conditions. Water is always water, whether it's the ice in your freezer, the liquid in your glass, or the steam rising from your tea. The triple point is just the moment when water gets to be its whole self all at once, before the universe insists it pick a side. Your eyes are reading these words right now, and in doing so, they're performing an extraordinary feat. The human eye can distinguish about 10 million different colors, 10 million variations in hue, saturation, and brightness. From the deep violet at the edge of perception to the warm reds that fire seems to radiate. From the subtle greens of a forest canopy to the countless shades of blue in a twilight sky. 10 million. But here's the peculiar truth. Most of what we call colors don't actually exist in any objective sense. They're not properties of the world, they're interpretations, constructions created by your brain when it processes electromagnetic radiation at different wavelengths. Out there in the world, there are just waves, light waves oscillating at different frequencies. Some waves are longer, some shorter, but the experience of red or blue, that happens inside your head. It's your brain's way of making sense of those wavelengths, of categorizing them into something useful for navigation and survival. Other animals see entirely different colors because their eyes have different receptors. Mantis shrimp, for instance, have 16 types of color receptors compared to our 3. What colors do they see? We literally cannot imagine them. They're experiencing wavelengths of light in ways that have no equivalent in human experience. And birds can see ultraviolet patterns on flowers and feathers that are completely invisible to us. So when you look at a sunset and think, that's beautiful, what you're really experiencing is your brain's particular interpretation of wavelengths between 620 and 750 nanometers. The beauty isn't in the light itself. It's in the way your mind translates it, gives it meaning, makes it something worth stopping to appreciate. Color is a conversation between the world and your consciousness, and the universe, obligingly, is singing a song we've learned to hear. Here's something to make you smile, perhaps. A gentle absurdity. Bananas are radioactive, naturally radioactive. They contain potassium-40, an isotope that undergoes radioactive decay, releasing a tiny amount of radiation every time it breaks down. Every banana you've ever eaten has been slightly radioactive. Every banana in every grocery store, in every kitchen, in every lunchbox is emitting radiation right now. But before you worry, consider this. You would need to eat about 10 million bananas at once to receive a fatal dose of radiation. 10 million. That's not a meal. That's not even a feast. That's an impossible mountain of fruit. Your breakfast banana is perfectly safe. The radiation it emits is so small, so insignificant, that your body doesn't even notice. In fact, you yourself are radioactive, containing potassium-40 and carbon-14 in your own tissues. We're all slightly radioactive. It's just part of being made of atoms in a universe where some atoms are unstable. There's even a unit of measurement called the banana equivalent dose, used to help people understand radiation exposure in everyday terms. A dental X-ray is about 5 bananas worth of radiation. A cross-country flight exposes you to about 400 banana equivalent doses. It's a whimsical way of making the abstract concrete, of helping us understand that radiation isn't some foreign danger, but part of the natural background of existence. So yes, bananas are radioactive. And isn't it somehow comforting to know that even something as ordinary as fruit participates in the universe's tendency toward transformation, toward change, toward the slow decay that powers stars and creates new elements? Everything is part of the same cosmic process, even your morning snack. Now, let's visit the largest living structure on Earth. The Great Barrier Reef stretches over 2,300 kilometers along the coast of Australia. It's so vast you can see it from space. A sprawling network of coral formations, islands, and underwater gardens visible even from orbit. But here's what makes it truly extraordinary. This entire structure, this monument to life, is built by creatures no bigger than a grain of rice. coral polyps. Billions of them, each one a tiny animal working in partnership with even tinier algae that live inside their tissues. The algae photosynthesize, providing food. The polyps, in return, provide shelter and access to sunlight. Together, they secrete calcium carbonate, building their skeletal homes one microscopic layer at a time, generation after generation, over thousands of years. These tiny architects have constructed something that dwarfs the pyramids, that rivals mountains in scale. It's a reminder of what's possible through accumulation, through patient, incremental effort repeated across time. One polyp doesn't build a reef, but millions of polyps, working unknowingly together, each contributing their tiny part, create something that becomes a world unto itself, a habitat for thousands of species, a structure that shapes ocean currents and weather patterns, a living monument visible from space, and it's fragile. Rising ocean temperatures are bleaching the coral, breaking the partnership between polyp and algae, causing sections of the reef to die. What took millennia to build can be damaged in years. It's a sobering thought, but also a call to attention, a reminder that even the grandest structures in nature are sustained by delicate balances, by conditions that must be maintained, by relationships that can break. Let's end this first set with something that happens inside you, right now, as you rest. Your stomach is filled with hydrochloric acid strong enough to dissolve metal. If you poured it on your skin, it would cause severe chemical burns. It's powerful enough to break down the toughest foods, to kill bacteria, to reduce a steak to amino acids. And it's sitting inside you, churning away, part of the everyday miracle of digestion. So why doesn't your stomach digest itself? What's protecting you from your own digestive power? The answer is mucus. Your stomach produces a new layer of protective mucus every 2 weeks, a barrier between the acid and the stomach wall. This mucus is thick enough, slippery enough, alkaline enough to neutralize the acid before it can cause damage. It's a shield, constantly renewed, constantly maintained. But sometimes the shield fails. Ulcers form when the mucus layer breaks down, allowing the acid to eat into the stomach lining. It's painful, dangerous, a reminder of how carefully balanced our internal chemistry really is. Your body is constantly working to maintain these balances, to protect itself from itself, to allow powerful processes while preventing them from running wild. It's happening right now as you lie there. Your stomach is producing acid, producing mucus, digesting whatever you ate hours ago, extracting nutrients, preparing waste for elimination. All of it automatic, all of it precise, all of it balanced on the edge between function and damage. Your body knows what it's doing. It's been doing this your entire life, every day, every hour, maintaining itself without your conscious thought. And tonight, as you drift towards sleep, it will continue its work, keeping you alive, keeping you together, protecting you from the very forces it uses to keep you fed. Lightning is a sculptor, though it works in glass rather than stone. When lightning strikes sand, whether on a beach, in a desert, or anywhere the conditions are right, something remarkable happens. The bolt carries temperatures of about 30,000 degrees Celsius, 5 times hotter than the surface of the sun. In the fraction of a second it takes for the lightning to discharge, that heat melts the sand along its path. The silica fuses instantly, and as the lightning travels downward into the ground, it creates hollow, branching tubes of glass that follow the exact path of the electrical discharge. These glass sculptures are called fulgurites, from the Latin word for lightning. They're fragile, delicate things, often extending several feet underground in twisting root-like patterns. Some are smooth inside, others rough and textured. Each one is unique, a perfect fossil of a moment of incredible energy, preserved in glass. If you could hold one, and some people do find them and carefully excavate them, you'd be holding the pathway of lightning itself. The negative space where electricity once flowed, now frozen in silica. It's a kind of natural art, created in an instant, preserved for millennia. Every storm that flashes across a beach might be, leaving these hidden sculptures beneath the sand, most of them never discovered, never seen, slowly eroding back into the grains they came from. There's something poetic about it. Lightning, which seems like pure destruction, pure discharge of energy, actually creates something beautiful in its wake. It leaves a signature, a record of its passage. Even violence, it seems, can make art. Here's a mystery of convergent evolution that baffles and delights. Koala bears have fingerprints. That's not particularly surprising. Many primates have them after all. But koala fingerprints are virtually indistinguishable from human fingerprints, even under a microscope. The whorls, loops, and arches are so similar that they could theoretically confuse a crime scene investigator. An expert would need to look very closely to tell them apart. But here's the extraordinary part. Koalas and humans are separated by about 70 million years of evolution. We didn't inherit fingerprints from a common ancestor. Who had them? Instead, both species independently evolved these intricate patterns, arriving at nearly identical solutions to the same problem: how to grip. Fingerprints, it turns out, aren't primarily for identification. They're functional. The ridges increase friction, allowing for better grip on branches, on tools, on whatever needs holding. But they also enhance our sense of touch, amplifying vibrations so our nerve endings can detect finer details of texture and shape. Koalas, who spend their lives climbing eucalyptus trees and need to carefully select leaves to eat, benefit from this same enhanced sensitivity. Nature, working independently on two completely different branches of the evolutionary tree, came up with the same solution, the same intricate pattern. It's like two architects working in different countries, never communicating, both designing buildings with the exact same floor plan because the mathematics of the problem demanded it. It makes you wonder what other solutions might be inevitable, what other patterns might emerge again and again, wherever life figures out similar problems. Perhaps certain designs are written into the fabric of possibility itself, waiting to be discovered by any species that needs them. Let's travel to Venus, that hellish, beautiful planet named for love. A day on Venus is longer than its year. Let that sink in for a moment. It takes Venus 243 Earth days to rotate once on its axis, to complete a single day-night cycle. But it only takes 225 Earth days to orbit the Sun, to complete a year. The planet completes its journey around the Sun before it finishes turning around once. This creates a strange temporal landscape. If you could somehow survive on Venus's surface, which you couldn't, given the crushing atmospheric pressure and temperatures hot enough to melt lead, you'd experience seasons changing before the day ended. The sun would move across the sky so slowly that you could walk faster than it, literally, outpacing the rotation of the planet. And Venus has another peculiarity. It rotates backward. Most planets spin in the same direction they orbit, counterclockwise when viewed from above the solar system's north pole. But Venus spins clockwise. Something in its history, perhaps a massive collision early in its formation, knocked it into this retrograde rotation. So on Venus, the sun rises in the west and sets in the east, taking months to do so. It's a world of inverted time, where the relationship between day and year, between rotation and orbit, operates under different rules than what we know. Standing on Venus, if you could stand there, would be disorienting in ways beyond the physical danger. Time itself would feel wrong, stretched and compressed in unfamiliar proportions. A reminder that the familiar rhythms of Earth, our 24-hour days, our 365-day years, aren't universal constants, but local circumstances, accidents of how our particular planet formed and evolved. In the frozen north, a small creature performs a miracle every winter. The wood frog can survive being frozen solid, not just cold, frozen. Ice crystals form throughout its body, in its blood, in the spaces between its cells. Up to 70% of the water in its body becomes ice. Its heart stops beating. Its lungs stop moving. Its brain ceases activity. By every measure we normally use, the frog is dead, but it isn't. Come spring, when temperatures rise, the frog thaws. Ice crystals melt. Blood begins to flow again. The heart resumes its rhythm. Within hours, the frog is hopping away, going about its business as if nothing extraordinary has happened, as if it hadn't just spent months as a frog-shaped ice sculpture. How is this possible? The frog produces natural antifreeze compounds, glucose and urea, that concentrate in its cells. These don't prevent freezing entirely, but they control where ice forms. The ice stays outside the cells, in the blood and surrounding spaces. The cells themselves remain protected, their delicate internal machinery preserved even while surrounded by ice. It's a chemical dance, a carefully orchestrated protection protocol evolved over millions of years. Other animals hibernate, slowing their metabolism, sleeping through winter. But the wood frog takes it further. It essentially dies and resurrects itself, crosses the boundary between life and death seasonally, as reliably as leaves falling from trees. It's a strategy so extreme, so unlikely, that it seems like it shouldn't work. And yet it does, year after year, in thousands of frogs across the northern reaches of North America. Perhaps death isn't always as final as we think. Perhaps life is more resilient, more clever, more determined than we give it credit for. The wood frog teaches us that the boundary between living and not living is more permeable than it seems, that nature has found ways to pause life and restart it, that survival can take forms we'd never imagine if we didn't see them with our own eyes. Chess, that ancient game of kings and strategy, contains more possibilities than the universe contains substance. After just 4 moves each, black and white each making 4 moves, there are more than 288 billion possible positions on the board. And that's just 4 moves into a game that might last 50, 60, or more. The total number of possible chess games has been estimated at 10 to the power of 120, a number so large it has its own name, the Shannon number, after Claude Shannon, who first calculated it. To put this in perspective, there are only about 10 to the power of 80 atoms in the observable universe. The possible chess games outnumber atoms by a factor of trillions of trillions of trillions. You could assign a unique chess game to every atom in the universe and still have unimaginably more games left over. This is what mathematicians call combinatorial explosion. Simple rules, 6 types of pieces, an 888 board, clear movement, restrictions, generate complexity that approaches infinity. You could play chess every second for the entire age of the universe and never repeat a game. Humanity could play continuously for billions of years and barely scratch the surface of what's possible. It's humbling, in a way. A game we invented, constrained by rules we chose, contains more variety than all the matter in existence. It suggests that complexity doesn't require vastness. It can emerge from simplicity, from constraints, from elegant rules applied recursively. And it means that every chess game ever played, every famous match, every casual game in a park is unique, has never happened before, will never happen again. Each one is a brief exploration of a tiny corner of an infinite landscape of possibility. Rain has a smell, you know it, that clean, earthy scent that rises when the first drops hit dry ground after a long drought. There's a word for it, petrichor. It comes from the Greek words for stone and the fluid that flows in the veins of the gods. Stone blood. It's a poetic name for a chemical process. During dry periods, plants release oils into the soil. These oils, along with other organic compounds, accumulate on rocks, on soil particles, on the surfaces of things. When rain comes, the water hits these surfaces and releases these oils into the air. The impact of the drops also creates aerosols, tiny particles suspended in the air, carrying these compounds with them. But there's another component to petrichor, geosmin, a compound produced by soil bacteria, particularly Actinomycetes. These bacteria thrive in soil, and when rain disturbs the earth, it releases spores and geosmin molecules into the air. Humans are extraordinarily sensitive to geosmin. We can detect it at concentrations as low as 5 parts per trillion. It's one of the most readily identifiable scents we know. Why are we so sensitive to it? Perhaps because, for our ancestors, the smell of rain meant water, meant life, meant survival. Those who could detect rain from a distance had an advantage, could find water sources, could prepare for the changes rain brings. The smell of petrichor might be written into our biology as a signal of hope, of renewal, of abundance after scarcity. So the next time you smell rain coming, you're detecting molecules released by plants and bacteria, carried on the wind, a chemical announcement that water is returning to the earth. It's not just a smell, it's information, a message from the ecosystem, a signal that all the organisms around you are responding to. You're part of that conversation, breathing in the language of life, responding to rain. Inside your skull, behind your eyes, an extraordinary thing is happening right now. Your brain generates about 20 watts of electrical power when you're awake. 20 watts. That's enough to power a dim light bulb, to charge a small device, to make a tiny motor spin. And all of it is being used for you, for processing, sensory information, for maintaining consciousness, for generating thoughts, for storing and retrieving memories, for coordinating the millions of processes that keep your body functioning. Despite representing only about 2% of your body weight, your brain consumes roughly 20% of your body's energy. It's metabolically expensive to run a brain. The neurons are constantly firing, constantly communicating, constantly maintaining the electrical gradients that allow them to send signals. Even at rest, even during sleep, the brain remains active, using nearly as much energy as when you're awake and alert. This is why thinking hard actually burns calories, why mental exhaustion is a real physical phenomenon. Your brain is working, burning glucose, generating heat, using resources. The wattage fluctuates throughout the day, higher when you're concentrating, lower when you're relaxed, but it never stops entirely. Even in the deepest sleep, your brain is using energy, processing the day's experiences, consolidating memories, maintaining your autonomic functions. 20 watts might not sound like much, but consider that this small amount of power is generating your entire subjective experience, all your thoughts, feelings, perceptions, memories. Every word you're reading right now, every image you're forming in your mind, every association you're making is powered by the electrical activity of neurons, by ions flowing across membranes, by synapses firing in patterns too complex to fully map. You are, in a very real sense, an electrical phenomenon, a pattern of energy moving through matter, aware of itself, contemplating its own existence. In the ocean, there exists a creature that would seem impossible if we hadn't found it. The mantis shrimp can punch with the speed of a .22 caliber bullet. Its club-like appendages accelerate at over 10,000 times the force of gravity, striking prey with such force that the water around the punch boils, literally boils, in a process called cavitation. The bubbles created by this cavitation collapse almost instantly, creating a second shock wave of force and even producing tiny flashes of light. The mantis shrimp then hits its prey twice with a single punch, once with the club itself, and again with the collapsing cavitation bubbles. But that's just its offense. Its vision is equally extraordinary. Mantis shrimp have 16 types of color receptors in their eyes, compared to the 3 we humans have. We can see red, green, and blue, and our brains combine these to create the full spectrum of color we perceive. But mantis shrimp can see ultraviolet light, infrared light, and polarized light. They can perceive a dimension of color that is completely inaccessible to us, completely unimaginable. What does the world look like to a mantis shrimp? We can't know. We literally cannot imagine it. It would be like trying to explain color to someone who has been blind from birth. There's no reference point, no shared experience to build understanding from. The mantis shrimp lives in a sensory world that is fundamentally different from ours, richer in dimensions we can't perceive. And this is happening in our own ocean, on our own planet, right now. Creatures are experiencing reality in ways that are forever closed to us, forever beyond our ability to know. It's a reminder of how limited our perception is, how much of reality passes us by simply because we don't have the receptors to detect it. We live in a narrow slice of the electromagnetic spectrum, aware of only a fraction of what's happening around us. And the mantis shrimp, with its impossible eyes and its bullet punch, sees and experiences far more. The coldest place in the universe isn't where you'd expect. It's not in the dark spaces between galaxies, not in the shadows of distant moons, not in the depths of space far from any star. The coldest place in the entire universe is here, on Earth, in a laboratory where scientists have managed to cool atoms to just a billionth of a degree above absolute zero. Absolute zero, 0 Kelvin, or 273.15 degrees Celsius, is the theoretical point where all atomic motion stops, where particles have the minimum possible energy. You can't reach it. The laws of thermodynamics prevent true absolute zero, but you can get extraordinarily close. Using lasers and magnetic fields, scientists trap atoms and slow them down, removing energy bit by bit, cooling them to temperatures that don't exist anywhere else in nature. At these temperatures, matter behaves strangely. Atoms begin to act less like particles and more like waves. Multiple atoms can occupy the same quantum state, forming what's called a Bose-Einstein condensate, a new state of matter that was only theoretical until we learned to reach these extreme temperatures. Time itself seems to slow at the quantum level. Particles exist in superpositions, probabilities become tangible, the boundaries of what's possible blur. It's colder in these laboratories than the cosmic microwave background radiation that fills all of space, the afterglow of the Big Bang itself. Outer space, despite its reputation for cold, is actually about 2.7 Kelvin, warmed by this ancient light. But humans, in their curiosity, have created conditions colder than anything the universe has produced naturally in 13.8 billion years. We reached the coldest point in existence, not through discovery, but through creation. We made it ourselves, through ingenuity and precision, through the application of quantum mechanics and laser physics. It's a strange achievement to create the ultimate cold, the deepest chill, here at home, in the warmth of our own world. Finally, for this set, something that challenges death itself. There is a jellyfish that might be immortal, Turritopsis dohrnii, the immortal jellyfish, has the ability to reverse its aging process. When it's stressed, injured, or simply old, it can transform its adult cells back into juvenile cells, essentially resetting its biological clock. It reverts to a polyp stage, a simpler, younger form, and then grows again into an adult jellyfish. And it can do this repeatedly, potentially forever. It's not that individual cells live forever. The cells still die and are replaced. But the organism as a whole can cycle back to the beginning, starting over, avoiding death through a kind of biological rebirth. Imagine if humans could do this. If, when we grew old, we could somehow revert to childhood and grow up again, retaining no memories but continuing in an endless loop of life. Of course, most Turritopsis dohrnii don't live forever in practice. They get eaten by predators, they succumb to disease, they die from environmental factors. Biological immortality doesn't grant invulnerability, but the potential is there, written into their cells, a capability that seems to defy one of the most fundamental aspects of life as we understand it, that living things age and die. What does this mean? Perhaps that aging isn't inevitable, that death isn't hardwired into biology, but is instead a feature that evolved, that serves some purpose, that could theoretically be reversed or eliminated. The immortal jellyfish proves that death's grip isn't absolute, that life has found at least one workaround, one escape clause in the contract we all seem to have signed. And as you lie there, contemplating the small, translucent creature drifting in the ocean, cycling through life again and again, maybe there's something comforting in knowing that life itself is more resilient, more inventive, more determined than we often think. It finds ways, it persists, it transforms death into renewal, ending into beginning, and continues on, impossibly, beautifully, through time. Your body is a universe unto itself, though perhaps not in the way you think. You contain about 37.2 trillion cells. That's an almost incomprehensible number. 37 followed by 12 zeros. Every cell a tiny factory, a complex system of membranes and proteins and genetic material working together to keep you alive. But here's the thing that shifts your perspective. You host even more bacterial cells than that. The microbes living on your skin, in your gut, in your mouth and lungs, they outnumber your own cells. In a very real sense, you are more bacteria than human. Or rather, you're a collaborative entity, a walking ecosystem where human cells and bacterial cells coexist in a relationship so intimate that neither could survive without the other. The bacteria in your gut help digest food, produce vitamins, train your immune system, even influence your mood through the chemicals they produce. Without them, you would die. You couldn't process nutrients properly, couldn't defend against pathogens, couldn't maintain the countless balances that health requires. We tend to think of ourselves as individuals, as single organisms, but that's an oversimplification. You're more like a community, a collective of trillions of organisms working together, sharing resources, communicating through chemical signals, maintaining a balance that keeps the whole system functioning. The bacteria aren't invaders or passengers. They're integral parts of who you are, so integrated that the boundary between you and them becomes philosophical rather than biological. And every person's microbial community is unique, shaped by diet, environment, genetics, even mood and stress levels. You're not just carrying DNA from your parents. You're carrying bacterial lineages that have been passed down through generations, modified by every meal you eat, every place you visit, every person you touch. Einstein showed us that time is not what it seems, not constant, not universal, not the steady metronome we imagine ticking away identically for everyone. Time moves slower for you when you're in motion compared to someone standing still. This isn't theory or abstraction. It's measurable, observable, and we account for it every day. GPS satellites orbit Earth at high speeds, and because of their motion, time passes slightly slower for them than it does for us on the ground. Without corrections for this time dilation, GPS would give us directions that are hundreds of feet off target. The system only works because we factor in Einstein's relativity. If you could travel at speeds approaching the speed of light, which you can't, but imagine, time would slow dramatically for you relative to people who remain stationary. You might experience a year while decades pass on Earth. You could travel to a distant star and return to find everyone you knew aged or gone while you remain young. It's called the twin paradox. One twin travels through space at high speed while the other stays home, and when they reunite, the traveler is younger. This isn't science fiction. It's reality, confirmed by countless experiments. Time is flexible, responsive to motion and gravity. it's woven together with space into a single fabric, space-time, that bends and stretches based on mass and velocity. Your personal time, your now, is slightly different from someone else's now if you're moving differently or experiencing different gravitational fields. So when you're sitting still reading this, time is flowing at one rate. But if you stood up and walked, time would flow infinitesimally slower for you than for someone remaining seated. The difference is tiny, unmeasurable in everyday life, but it's real. Time itself adjusts based on what you're doing. The Pacific Ocean is so vast that it contains a peculiar geometric property. There are points in the Pacific where, if you drilled straight down through the earth and emerged on the opposite side, at the antipode, the point directly opposite on the globe, you would still be in the Pacific Ocean. The ocean is so large that it exists on both sides of the planet simultaneously. No other ocean can claim this. The Atlantic, the Indian, the Arctic, all of them have antipodes that are on land, but the Pacific wraps so far around the earth that it meets itself on the other side. This gives the Pacific a strange quality of encompassing. It's not just large, it's larger than all the land on Earth combined. It covers more than 30% of the planet's surface, more than all the continents together. If you gathered all the land masses and tried to fit them into the Pacific, they would all fit with room to spare. Standing on a beach on the western coast of South America, looking out at the water, you're gazing at an ocean that stretches nearly halfway around the world before it reaches Asia. And even then, it continues, wrapping around until it touches those same shores from the opposite direction. The Pacific is less like an ocean and more like the ocean, with other bodies of water as smaller siblings scattered around its edges. The early Polynesian navigators understood this vastness intimately. They crossed thousands of miles of open water in canoes, navigating by stars and waves and birds, settling islands separated by distances that seem impossible to traverse without modern technology. They lived on an ocean planet where land was the exception and water was the rule. Plants can hear, not with ears, not with any organ that resembles what we call hearing, but they can detect vibrations and respond to them. Scientists discovered this by playing recordings of water flowing through pipes near plant roots. The plants grew their roots toward the sound, even when there was no actual water present, just the recording. They were detecting the vibrations of what sounded like water and moving toward it, demonstrating a form of acoustic perception that predates animals by hundreds of millions of years. This suggests that plants have been listening to their environment far longer than we've existed. They sense vibrations in the soil, from water flowing underground, from insects moving nearby, perhaps from other plants. They use this information to make decisions about where to grow, when to defend themselves, how to allocate resources. It's not consciousness as we understand it, but it is responsiveness, awareness of a sort, a relationship with sound that we're only beginning to understand. Other experiments have shown that plants respond to the vibrations of insects chewing on their leaves. They can distinguish between the sound of a caterpillar eating and the sound of wind blowing, and they respond differently to each. When they detect the chewing vibrations, they increase production of defensive chemicals. They're not just passively waiting to be eaten, they're actively listening for threats and mounting defenses. What does this mean for our understanding of plants? Perhaps they're more dynamic, more interactive with their environment than we've given them credit for. Perhaps the line between sensing and awareness, between reaction and perception, is blurrier than we thought. Plants might not think, but they listen, they respond, they make choices based on information gathered through senses we didn't know they had. Your nose is performing an almost magical feat of discrimination right now, though you're probably not aware of it. The human nose can detect over 1 trillion different scents, 1 trillion distinct odors, each combination of molecules creating a unique sensory experience. This is far more than we previously believed. Early estimates suggested maybe 10,000 different scents, but more recent research has shown our olfactory capability is orders of magnitude greater. This sensitivity rivals, and perhaps exceeds, our vaunted sense of sight. We can distinguish about 10 million colors, which seems impressive until you realize we can distinguish 100,000 times more smells. Scent is the sense we undervalue, the one we think of as primitive, animalistic, less refined than vision or hearing. But in terms of pure discriminatory power, it might be our most sophisticated sense. How does it work? Your nose contains about 400 types of olfactory receptors, each sensitive to different molecular shapes and features. When molecules enter your nose, they bind to these receptors in various combinations, creating a pattern of activation. Your brain interprets these patterns as distinct smells. The number of possible combinations is astronomical, which is why we can detect so many different odors. And smell is deeply connected to memory and emotion in ways that other senses aren't. The olfactory bulb, which processes smell, is directly connected to the hippocampus and amygdala, brain structures involved in memory and emotion. This is why a particular scent can instantly transport you to a specific moment in your past, complete with the emotions you felt then. Smell bypasses the cognitive processing that other senses go through, hitting memory and emotion directly. So that trillion scent capability isn't just for detecting food or danger, it's for building a rich, textured emotional relationship with the world, for embedding experiences in memory, for connecting past and present through invisible molecules floating through the air. Every hydrogen atom in your body is 13.8 billion years old as the universe itself. In the first few minutes after the Big Bang, as the universe expanded and cooled from its initial infinitely hot, infinitely dense state, conditions became right for the first atomic nuclei to form. Protons and neutrons combined to create hydrogen and helium nuclei in a process called Big Bang nucleosynthesis. The hydrogen atoms formed then, in those first 3 minutes of existence, are the same hydrogen atoms that exist now, scattered throughout the universe, some of them now part of you. Those atoms have journeyed through unimaginable time and space. They've been part of nebulae, collapsed into stars, been fused into heavier elements, and then scattered again by supernovae. They've drifted through galaxies, condensed into new stellar systems, become part of planets, dissolved in ancient oceans, been absorbed by primitive organisms, cycled through ecosystems for billions of years, And now, some of them are here, in you, part of your cells, part of your water, part of your DNA. The heavier elements in your body, the carbon, nitrogen, oxygen, all the elements heavier than helium, were forged in stars, created through nuclear fusion in stellar cores, then released into space when those stars died. Carl Sagan famously said we are made of star stuff, and he was precisely right. The iron in your blood, the calcium in your bones, the oxygen you're breathing, all of it was created inside stars that lived and died before our sun even existed. You are, quite literally, the universe experiencing itself. Ancient atoms forged in the first moments of existence and in the hearts of long-dead stars, temporarily arranged in a pattern that can think, feel, and wonder about its own origins. It's enough to make you feel both infinitely small and cosmically significant. The Earth has a magnetic field that protects us, guides birds on migration, allows compasses to point north, but this field isn't stable. It moves, it weakens and strengthens, and periodically it flips. The magnetic poles have reversed many times throughout Earth's history. North becomes south, south becomes north, and the transition takes thousands of years. During the flip, the magnetic field weakens significantly, sometimes dropping to just 10% of its normal strength. The last reversal occurred about 780,000 years ago, and we might be overdue for the next one, though predicting these events is difficult. What happens during a reversal? The magnetic field doesn't disappear entirely. It becomes chaotic, multipolar, with multiple north and south poles appearing at different locations before eventually settling into a new configuration. Animals that navigate by magnetism would become confused. Satellites and electrical grids could be affected by increased solar radiation reaching the surface. It wouldn't be apocalyptic, but it would be disruptive. A planetary-scale reorganization of invisible forces. We know these reversals happen because rocks preserve the direction of the magnetic field when they form. Ancient lava flows as they cooled, locked in the orientation of the Earth's magnetic field at that time. By studying these rocks, we can reconstruct the history of magnetic reversals stretching back hundreds of millions of years. The pattern is irregular. Sometimes reversals happen every few 100,000 years. Other times, millions of years pass between flips. What causes them? The Earth's core, a ball of solid iron surrounded by liquid iron, generates the magnetic field through its motion. The liquid iron flows in complex patterns driven by heat and the Earth's rotation. When these flow patterns become unstable, the magnetic field can reorganize itself, flipping the poles. It's a reminder that even the most stable-seeming features of our planet are temporary, cycling through changes on timescales far longer than human civilizations. There is a creature so resilient, so improbably tough, that it can survive conditions that would destroy virtually any other form of life. The tardigrade, also called a water bear because of its stumbling gait, is barely visible to the naked eye, about 0.5 millimeter long. It looks almost comical, like a microscopic bear with 8 legs, bumbling through wet moss and lichen. But this tiny creature is the toughest organism we know. It can survive the vacuum of space. It can withstand radiation doses hundreds of times stronger than would kill a human. It can be cooled to nearly absolute zero or heated to 150 degrees Celsius. It can go without water for decades. How? When conditions become unfavorable, tardigrades enter a state called cryptobiosis. They retract their legs, lose up to 95% of their body water, and essentially shut down all metabolic processes. In this state, they're not quite alive in the traditional sense. They're suspended, paused, waiting, and they can remain paused for years, even decades, until conditions improve. Add water, and they rehydrate, resume metabolism, and continue living as if nothing happened. This isn't just dormancy. It's a complete cessation of life processes, a crossing into a state that blurs the line between living and non-living, and yet they come back, intact, functional, ready to reproduce and continue their lineage. Scientists have revived tardigrades that were frozen for 30 years. They've sent them to space and brought them back alive. They've subjected them to pressures that would crush most organisms, and the tardigrades survived. What does this tell us about life? Perhaps that it's more adaptable, more resilient, more determined than we imagine. Perhaps the forms of life we know, warm, wet, oxygen-breathing, are just one narrow band in a much wider spectrum of possibility. The tardigrade shows us that life can persist in conditions we'd call impossible, that the boundaries of the habitable zone are wider than we thought. Color doesn't exist in nature, not in the way we experience it anyway. Out in the world, there are electromagnetic waves oscillating at different frequencies. Some waves have long wavelengths, some short. They're all the same phenomenon, light, just vibrating at different rates. But red and blue as experiences, as qualities, as the felt sensation of seeing color, that only exists inside your brain. It's a translation, an interpretation your visual system creates to make sense of different wavelengths. Other animals with different photoreceptors create different interpretations. A bee sees ultraviolet patterns on flowers that are invisible to us, patterns that guide them to nectar. A dog sees fewer colors than we do, living in a world of blues and yellows without our reds and greens. A mantis shrimp, as we mentioned earlier, sees colors we cannot even imagine because it processes light in ways our brains aren't equipped to handle. So when you look at a sunset and see orange and pink and purple bleeding across the sky, you're seeing your brain's particular interpretation of photons scattered by atmospheric particles. The photons themselves have no color. They're just energy vibrating at specific frequencies. Color is what your consciousness does with that information, the way it paints reality to make it navigable, meaningful, beautiful. This means that the universe, stripped of observers, might be fundamentally colorless. Just waves of energy moving through space, interacting with matter, bouncing and refracting and absorbing, but never being red or blue, until some conscious being looks and creates those experiences through neural processing. Color is a collaboration between the world and the mind, and the beauty we see in it is something we bring to the universe, not something we find there waiting for us. There are more trees on Earth than stars in the Milky Way galaxy. Scientists estimate approximately 3 trillion trees currently exist on our planet. The Milky Way, our home galaxy, contains somewhere between 100 and 400 billion stars. Even taking the high estimate for stars, trees outnumber them by a factor of 7 or 8. It's a perspective shift. We think of the cosmos as vast and Earth as small. But in terms of discrete objects, our planet hosts more trees than our galaxy hosts stars. But this hasn't always been the case. Before humans developed agriculture and civilization, there were approximately 6 trillion trees, twice as many as today. We've cut down nearly half the trees that once existed, clearing forests for farmland, for cities, for resources. The tree population has been roughly halved in just a few thousand years of human activity. Trees are extraordinary organisms. They can live for thousands of years. Some bristle-cone pines are over 5,000 years old, alive when the pyramids were being built. They create their own ecosystems, hosting birds and insects and fungi and lichens. They pull carbon dioxide from the air and store it as wood, acting as carbon sinks that help regulate the atmosphere. They communicate through fungal networks, share resources with their young, respond to threats by producing defensive chemicals. And yet we're removing them faster than they can regenerate. Not everywhere. Some places are reforesting. Some countries are planting extensively. But globally, the trend has been toward fewer trees, less forest, more cleared land. Those 3 trillion trees are an enormous number, but it's half of what once was, and declining. Every tree represents decades or centuries of growth, a unique ecological niche, a home for countless organisms. When we remove them, we're not just taking wood, we're dismantling communities, erasing carbon storage, simplifying ecosystems. Here's something to contemplate. As you drift toward sleep, the probability that you exist at all is so small, it's essentially zero. Think about all the events that had to occur for you to be here. Your parents had to meet, out of all the billions of people who have ever lived. Those 2 specific individuals had to cross paths at exactly the right moment. And before that, their parents had to meet, and their parents before them. Going back through generations, through centuries, through millennia, every single one of your ancestors had to survive long enough to reproduce, had to find a partner, had to conceive at precisely the right moment for that specific sperm to meet that specific egg. One mathematician attempted to calculate these odds. He considered just your ancestry going back to the beginning of humanity, not even including the evolutionary history before that, and arrived at a probability of approximately 1 in 10 to the power of 2,685,000. That's a 1 followed by over 2.5 million zeros. It's a number so small that it's functionally indistinguishable from impossible. And yet here you are. Improbable doesn't mean impossible. It just means unlikely. You are the result of an unbroken chain of survival and reproduction stretching back 4 billion years, back to the first self-replicating molecules in ancient oceans. Every organism in your lineage survived long enough to pass on its genetic material. Every single one. Not one of your ancestors died in childhood. Not one failed to find a mate. Not one was eaten or starved or struck by disease before reproducing. You're a statistical miracle, a winning lottery ticket in a game with more tickets than there are atoms in the universe. And everyone else is too. Every person you've ever met, every stranger on the street, represents the same impossible chain of chances that somehow all fell into place. We're all improbable, all here against astronomical odds, all carrying forward the legacy of countless generations who survived when they might easily have perished. Sound, which we think of as something that travels through air, can do something that seems to defy gravity itself. Sound waves can levitate objects. It's called acoustic levitation, and it works through the interference of sound waves. When sound waves moving in opposite directions meet, they create standing waves, patterns of constructive and destructive interference that remain stationary in space. At certain points in these standing waves, called nodes, the pressure remains constant, and if you position a small object at one of these nodes, it will float there, suspended by nothing but sound. It's not magic, it's physics. The pressure variations above and below the object balance out, creating a stable position where the object can hover without support. Scientists have used this technique to levitate drops of liquid, small solid objects, even living insects, all held in mid-air by carefully controlled sound waves. The objects don't just hover, they can be moved by adjusting the sound field, manipulated without touch, controlled by pure vibration. This has practical applications. In laboratories, acoustic levitation allows scientists to study materials without contamination from containers. Liquids can be held and examined in their pure state without touching walls that might affect their properties. It's also being explored for manufacturing processes, for drug development, even for potential applications in space where traditional containers are problematic. But there's also something almost magical about it, something that speaks to our intuitions about the intangible nature of sound. We can't see sound waves, can't touch them, can't hold them. They seem ephemeral, powerless compared to solid matter. Yet here they are, strong enough to counter gravity, to hold objects suspended in space. It's a reminder that the invisible forces around us, sound, electromagnetic fields, gravity itself, are as real and powerful as anything we can touch. While you sleep tonight, your brain will be more active than it is during much of your waking day. It seems counterintuitive. Sleep feels like rest, like shutdown, like the brain taking a break from the work of consciousness. But measurements of brain activity tell a different story. During certain stages of sleep, particularly REM sleep when dreams occur, your brain uses as much energy and shows as much neural activity as when you're awake and alert. In some regions, activity actually increases during sleep. What's your brain doing with all this energy? It's consolidating memories, transferring information from short-term to long-term storage, deciding what to keep and what to discard from the day's experiences. It's processing emotions, integrating new experiences with old knowledge, making connections that might not be obvious during waking hours. It's cleaning house, literally washing away metabolic waste products through the glymphatic system. A waste clearance process that operates primarily during sleep. Your brain is also running simulations, playing out scenarios, solving problems. Many famous insights and discoveries have occurred during sleep or immediately upon waking. The structure of the benzene molecule, discovered in a dream about a snake biting its tail. The tune to Yesterday, which Paul McCartney heard complete in a dream. Mathematical proofs worked out by sleeping minds. Sleep isn't just rest, it's a different mode of cognitive processing, one that might be essential for creativity and problem solving. So as you lie there, as consciousness fades and you slip into sleep, know that your brain isn't shutting down. It's shifting gears, moving into a different kind of work, processing and consolidating and creating in ways that waking consciousness can't manage. Sleep is active, productive, essential. It's not time lost. It's time invested in maintaining the extraordinary organ that makes you who you are. Glass is one of the most familiar materials in modern life, yet its nature remains subtly strange. Technically, glass is not a solid in the conventional sense. It's an amorphous solid, or what physicists sometimes call a supercooled liquid. Unlike crystalline solids, where atoms are arranged in regular, repeating patterns, the atoms in glass are arranged randomly, more like a liquid than a solid. Glass forms when molten material cools so quickly that the atoms don't have time to arrange themselves into crystal structures. They freeze in place, maintaining their disordered arrangement. This has led to a persistent myth that glass windows in old buildings are thicker at the bottom because the glass has flowed downward over centuries. It's not true. Old glass is thicker at the bottom because of manufacturing processes, not because it flowed. Glass does flow, but so slowly that no measurable change would occur over human timescales. To see glass flow, you'd need to wait millions of years. For practical purposes, it's solid, but theoretically, fundamentally, it's a liquid frozen in time. What's interesting is that glass represents an intermediate state, caught between order and chaos, between solid and liquid. It's matter that couldn't decide what to be, that got stuck in transition. And this gives it unique properties: transparency, smoothness, the ability to be molded when hot but rigid when cool. These properties have shaped human civilization, giving us windows, lenses, fiber optics, screens, containers, art. We look through glass every day without thinking about how strange it is. This material that's neither quite solid nor liquid, that exists in a perpetual state of almost but not quite crystallization, that holds its shape against gravity for timescales far exceeding human existence, but still, technically, flows. It's familiar and alien at once, ordinary and impossible, a frozen river of silicon dioxide through which we observe the world. The sun is losing mass. Right now, as you read this, it's getting lighter. Every second, the sun converts about 4 million tons of its mass into energy through nuclear fusion. Hydrogen atoms in the core are squeezed together by immense pressure and temperature until they fuse into helium, and in the process, a tiny amount of mass disappears, converted entirely into energy according to Einstein's famous equation, E.mc2. That energy radiates outward, eventually reaching Earth as sunlight, warming our planet, driving photosynthesis, powering weather systems, making life possible. 4 million tons per second sounds like an enormous loss, and it is. Over the course of a year, the sun loses about 126 trillion tons of mass. But the sun is so massive that this loss is negligible. It contains about 2 x 1030 kilograms of mass. That's a 2 followed by 30 zeros. At its current rate of mass loss, the sun has enough fuel to continue shining for another 5 billion years before it exhausts its hydrogen supply and begins the process of dying, swelling into a red giant, and eventually shedding its outer layers. This mass loss is what makes existence possible. The sun's mass, converted to energy, is the ultimate source of almost all energy on Earth. The food you eat, the warmth you feel, the fossil fuels we burn, all of it traces back to sunlight, to the sun's ongoing conversion of mass into energy. You are, quite literally, sustained by the sun's slow self-consumption, by the gradual transformation of stellar matter into the light that powers our world. And when the sun finally runs out of hydrogen, when fusion slows and eventually stops, it will have converted only about 0.07% of its total mass into energy over its 10 billion year lifetime. A tiny fraction, yet enough to sustain a planet full of life for billions of years. Inside each of your cells, there's a molecule that contains your complete genetic blueprint, and if you could unravel it, it would be almost incomprehensibly long. DNA in a single human cell, if stretched out end to end, would measure about 6 feet, roughly 2 meters. That's remarkable enough. But you have trillions of cells, each containing this same 6 feet of DNA. If you could unravel and connect all the DNA in your body, it would stretch approximately 10 billion miles. That's enough to reach from Earth to Pluto and back, twice. All of it packed into a body that's only a few feet tall. How is this possible? Through extraordinary levels of organization and compaction. DNA is wrapped around proteins called histones, which are bundled into chromatin, which is further coiled and condensed into chromosomes. It's packaging within packaging within packaging, origami at the molecular level, allowing immense length to fit into microscopic space. Each cell nucleus, invisible to the naked eye, contains this precisely folded library of information. And this isn't just storage, it's active, functional information. Sections of DNA are constantly being accessed, transcribed into RNA, translated into proteins. The cell is reading its instruction manual in real time, producing the molecules it needs based on current conditions. Genes turn on and off, responding to signals, adjusting production, maintaining the delicate balance of cellular chemistry. The information density is staggering. Your genome contains about 3 billion base pairs, 3 billion letters in the genetic code. If you tried to type it out, 1 letter per second, it would take you nearly a century. And every time a cell divides, it copies this entire library with remarkable accuracy, making only about 1 error per billion base pairs. It's molecular machinery operating at a level of precision that human technology still struggles to match. The Amazon rainforest is often called the lungs of the earth, producing about 20% of the world's oxygen. It's a compelling metaphor, but the reality is more complex and perhaps more interesting. Yes, the Amazon produces enormous amounts of oxygen through photosynthesis. All those trees, all that vegetation, constantly converting carbon dioxide and water into glucose and oxygen, releasing breathable air into the atmosphere. But here's what's often left out. The rainforest also consumes nearly all of that oxygen through respiration. The trees breathe, the animals breathe, the bacteria and fungi in the soil breathe. When organic matter decays, it consumes oxygen. The net oxygen contribution from the Amazon, the amount it adds to the atmosphere after accounting for all consumption, is close to 0. So where does our oxygen actually come from? Mostly from the ocean. Phytoplankton, microscopic photosynthetic organisms drifting in the surface waters, produce an estimated 50–80% of Earth's oxygen. These invisible gardens, these floating forests of single-celled organisms, are the true lungs of the planet. They're more abundant than trees, more productive than rainforests, and essential to maintaining the atmospheric balance that makes complex life possible. This doesn't diminish the Amazon's importance. The rainforest is crucial for regulating climate, storing carbon, maintaining water cycles, and hosting perhaps the greatest concentration of biodiversity on the planet. But its role is different from what the lungs metaphor suggests. It's more like a carbon bank than an oxygen factory, holding vast amounts of carbon in its trees and soil, preventing it from entering the atmosphere as carbon dioxide. Understanding this matters because it changes how we think about conservation. Protecting the Amazon isn't primarily about oxygen production. It's about preserving ecosystems, preventing carbon release, maintaining rainfall patterns, protecting species. The ocean's phytoplankton, meanwhile, deserve more attention than they typically receive. These microscopic organisms that actually do breathe for the planet. Einstein found quantum entanglement so troubling that he called it spooky action at a distance and spent years trying to prove it couldn't be real. He was wrong. It's real, and it challenges everything we think we understand about how reality works. When two particles become entangled through various quantum processes, they remain connected in a profound way, no matter how far apart they are. Measure the state of one particle, and you instantly know the state of the other, even if they're separated by light years. Change one, and the other changes correspondingly, immediately, with no signal passing between them. No delay for light to travel the distance. This seems to violate the cosmic speed limit. Einstein proved that nothing can travel faster than light, that information cannot be transmitted instantaneously across space. Yet entangled particles appear to do exactly this, coordinating their behavior instantly across any distance. It's as if the separation between them is illusory, as if distance doesn't apply at the quantum level the way it does in our everyday experience. The key insight is that entanglement doesn't allow you to send messages faster than light. You can't control what state your particle will have, so you can't encode information in it. The correlation exists, but it's only visible after you compare measurements from both particles, and that comparison requires classical communication, which is limited by the speed of light. So causality is preserved, even as our intuitions about separateness and locality are violated. What does it mean? Perhaps that the universe is more deeply connected than we imagine, that separation is a macroscopic illusion, that at the quantum level everything remains entangled with everything it's ever interacted with. We're left with a reality that's non-local, interconnected in ways that seem impossible but are demonstrably true. Einstein was disturbed by this because it suggested the universe is fundamentally strange, fundamentally unlike our everyday experience. He was right to be disturbed. It is strange, beautifully, impossibly strange. Your genome contains about 3 billion base pairs, 3 billion letters of genetic code that spell out the instructions for building and maintaining you. But only about 2% of that code actually gets translated into proteins, the molecules that do most of the work in your cells. The rest was once dismissively called junk DNA, leftovers from evolution, non-functional sequences that accumulated over time, but served no purpose. It seemed like noise in the signal, like blank pages scattered through an instruction manual. But we're discovering that this junk isn't junk at all. Much of it plays crucial regulatory roles, controlling when genes turn on and off, how much protein they produce, how cells differentiate and specialize. These non-coding regions contain switches and dimmers and timers, controlling the expression of genes in response to environmental conditions, developmental stages, cellular needs. They're like the stage directions in a play, not the dialogue itself, but essential instructions for how the dialogue should be delivered, when actors should enter and exit, how scenes should be lit and paced. Without these regulatory sequences, the genes wouldn't know when or where to act. There are also sequences that seem to be remnants of ancient viral infections, retroviruses that inserted themselves into our ancestors' genomes millions of years ago and got passed down through generations. Some of these viral sequences have been co-opted for useful purposes, repurposed by evolution into functional parts of our biology. Others remain dormant, fossil evidence of past infections carried in every cell. The genome is less like a simple instruction manual and more like a library, containing not just current instructions, but historical records, regulatory frameworks, backup systems, and elements whose functions we're still discovering. We're learning that the organization and regulation of genetic information is as important as the information itself, that complexity emerges not just from what genes you have, but from how and when they're used. On Neptune and Uranus, the two ice giants of our outer solar system, it rains diamonds. Deep in their atmospheres, where pressure becomes intense and temperatures soar despite the planet's distance from the sun, methane gas is compressed and heated until its carbon atoms crystallize into diamond. These diamonds, some perhaps as large as hailstones, fall slowly through layers of liquid hydrogen and helium, eventually sinking toward the planet's rocky cores. Scientists estimate that thousands of tons of diamonds rain down on these planets every year, accumulating over billions of years into layers of diamond, perhaps thousands of miles thick. This isn't speculation. It's based on laboratory experiments where scientists recreated the pressure and temperature conditions found in these planets' interiors. They found that hydrocarbons break down and reform into diamond under these conditions, exactly as theory predicted. The universe, it turns out, makes diamonds far more casually than we do on Earth, where they form in the extreme conditions of the mantle and are brought to the surface only rarely by volcanic activity. On Neptune and Uranus, diamonds are weather. They're precipitation, falling through atmospheres of exotic chemistry and extreme conditions, part of the planet's natural circulation. The cores of these planets might be surrounded by oceans of liquid diamond, or perhaps giant diamond icebergs floating in seas of liquid carbon. We can't observe these interiors directly. They're too distant, too hostile to any probe we could build. But the physics is clear. Diamond rain is real, happening right now, on worlds orbiting our sun. It's a reminder that rarity and value are local, contextual. On Earth, diamonds are precious because they're difficult to find and extract. On Neptune, they're as common as rain, falling continuously through alien skies, worthless except as products of chemistry and pressure. beautiful in their abundance rather than their scarcity. The heart of a blue whale is an organ of such extraordinary scale that it borders on the fantastical. It weighs approximately 400 pounds, as much as a large motorcycle or grand piano. It's roughly the size of a small car, large enough that a human could theoretically swim through its aorta, the main artery that carries oxygenated blood from the heart to the rest of the body. This massive organ beats only 5 to 6 times per minute when the whale is diving deep, conserving energy in the cold, oxygen-poor depths. Yet each beat is powerful enough to circulate 10,000 pounds of blood through a body that can weigh up to 200 tons. Blue whales are the largest animals to have ever lived on Earth. Larger than any dinosaur, larger than any creature in the fossil record. They can grow to over 100 feet long, and their tongues alone can weigh as much as an elephant. Everything about them exists at a scale that seems to push against the limits of what biology can achieve, what physics allows, what evolution can produce. And yet they survive on some of the smallest organisms in the ocean. Blue whales are filter feeders, consuming tiny krill, shrimp-like creatures barely a few centimeters long. They take in enormous mouthfuls of water, then push it out through baleen plates, trapping the krill inside. A single whale might eat 4 tons of krill per day. Millions of individual organisms, all to fuel a body that operates at the absolute upper limit of what warm-blooded life can sustain. There's something almost poetic about it. The largest heart in the world, beating slowly in the largest body that's ever existed, sustained by some of the smallest animals in the sea. Scale operates in strange ways in the ocean, where buoyancy eliminates many of the constraints that limit size on land. Blue whales remind us that life, given the right conditions, can grow to proportions that seem impossible, creating living monuments to the power of evolution and adaptation. Light from the sun reaches Earth in about 8 minutes, traveling at 186,000 miles per second across 93 million miles of space. It seems instantaneous on human timescales, but that light's journey actually began much, much earlier. The photons that strike your skin on a sunny day, that warm your face and make you squint, were created in the sun's core through nuclear fusion. But they didn't travel directly from core to surface. The sun is so dense, so packed with matter, that photons can't move in straight lines. They're constantly absorbed and re-emitted by atoms, taking random walk paths through the solar interior. Each photon bounces countless times, moving only tiny distances before being absorbed again, redirected, absorbed again, over and over. Scientists estimate that it takes between 10,000 and 170,000 years for a photon to travel from the sun's core to its surface, a distance of only about 430,000 miles. The same photon that crosses 93 million miles of empty space in 8 minutes spends tens of thousands of years crossing less than 1 million miles of dense solar plasma. It's a journey measured not in distance, but in interactions, in the countless collisions that gradually, randomly, eventually carry the photon outward. Once it reaches the surface, though, the photon is free. It streams away at the speed of light, crossing the void to Earth in those 8 quick minutes, bringing energy that was locked in hydrogen nuclei before humans existed, before recorded history, before civilization, before our species emerged. The sunlight touching you right now is ancient and new at once, born in fusion tens of thousands of years ago, but only now completing its journey. It's a reminder that even light, the fastest thing in existence, can be slowed, detained, forced to take the long way. And that the sun's energy, which seems so immediate and present, carries a hidden history of patient wandering through stellar depths before finally arriving here. If you could somehow gather all the elements that make up your body and separate them by type, you'd find you contain quite a bit of chemistry. Your body has enough carbon to make about 900 pencils. All the graphite in 900 standard pencils could be extracted from your carbon atoms. There's enough iron to forge a 3-inch nail, enough sulfur to kill the fleas on a large dog, enough lime to whitewash a small chicken coop, and enough phosphorus to make 2,200 match heads. You contain about 20 grams of magnesium, 140 grams of potassium, and enough fat to make 7 bars of soap. But here's the extraordinary thing. None of these elements were created on Earth. All of them, except hydrogen, were forged in stars billions of years before our solar system existed. Carbon was created in the triple alpha process, in red giant stars. Iron was made in supernovae, in those final explosive moments when massive stars died. Oxygen, nitrogen, calcium, phosphorus, all of them were created in stellar cores or supernova explosions, then scattered into space when those stars died. This stellar matter drifted through the galaxy for millions or billions of years, eventually condensing into new solar systems, including ours. It became part of the nebula that collapsed to form the sun and planets. Some of it ended up on Earth, incorporated into rocks and water and eventually into living organisms. And now some of those ancient atoms, created in long dead stars, are temporarily part of you. You are literally made of stardust, not metaphorically, literally. The iron in your blood, allowing it to carry oxygen, the calcium in your bones, giving them structure, the carbon in your DNA, encoding your genetic information. All of it was forged in stellar furnaces, then traveled through space and time to become part of you, temporarily, before being recycled again when you die, continuing the cosmic circulation of matter that's been ongoing since the first stars formed. Crows are remarkably intelligent birds, but their cognitive abilities extend into territory that seems almost human. They can recognize individual human faces and hold grudges for years. Researchers discovered this through experiments where they wore masks while capturing and banding wild crows. The crows, understandably upset by the experience, remembered the faces on those specific masks. Years later, when researchers wore the same masks again, the crows would scold and dive-bomb them. Even though the researchers had done nothing threatening recently, crows wearing different masks or no masks at all could walk through the same area without incident. The crows had learned specific faces and associated them with danger. But it gets more interesting. The crows who had never been captured themselves also learned to fear these masks. The original victims had somehow taught other crows in their social group which faces to distrust. This knowledge spread through the crow population. Young crows who weren't even alive during the original captures learned to scold the masked researchers. The grudge was being passed down almost culturally through Crow society. This suggests a level of social learning and communication that we don't fully understand. Crows can apparently describe threats to each other in sufficient detail that other crows can recognize those threats. They maintain long-term memories of individuals who wronged them. They teach their young which humans to distrust. They hold grudges and spread them socially. It's both impressive and slightly unnerving. Next time you encounter a crow, consider that it might be watching you, assessing you, possibly remembering you, and if you do something it doesn't like, it might tell its friends, its family, its entire social network. Crows are intelligent, social, and possess memory and communication abilities that blur the lines we like to draw between human and animal cognition. They're watching us more carefully than we usually realize. The universe is expanding. That's been known since 1929, when Edwin Hubble discovered that distant galaxies are moving away from us. But in 1998, astronomers made a shocking discovery. The expansion is accelerating. Galaxies aren't just moving apart because of momentum from the Big Bang. They're moving apart faster now than they were in the past. Something is pushing them, driving the expansion to speed up rather than slow down as gravity should cause it to. We call this something dark energy, though the name is more admission of ignorance than explanation. We don't know what it is, what causes it, or why it exists. Dark energy makes up about 68% of the total energy content of the universe. Dark matter, another mysterious substance we can't directly detect, accounts for about 27%. The ordinary matter that makes up stars, planets, and us, everything we can see and touch, constitutes only about 5% of the universe. We live in a cosmos where 95% of everything is invisible, detectable only through its gravitational effects and its influence on the expansion rate. This accelerating expansion has profound implications. It means that distant galaxy clusters are moving away from us faster than light can travel, so we'll never be able to reach them or communicate with them. The observable universe will actually shrink over time as more and more distant objects cross the boundary where their recession velocity exceeds light speed. In the far future, any civilizations that exist will see a much emptier universe, with only their local galaxy cluster visible and the rest lost beyond an unreachable horizon. Dark energy is pushing the universe apart, and we don't know why, don't know what it is, don't know if it will continue forever or change over time. We're living in a cosmos where the majority of everything is a mystery, where the dominant force shaping the universe's fate is something we can barely describe, let alone understand. Your brain processes visual information with stunning speed, faster than you consciously realize. Studies have shown that the brain can process and identify images in as little as 13 milliseconds. That's 13 thousandths of a second, a duration so brief it's hard to conceptualize. In that tiny slice of time, your visual cortex receives signals from your eyes, processes the patterns of light and dark, identifies edges and shapes, recognizes objects, and begins forming meaning. You can see and understand an image faster than you can blink, which takes about 100 or 150 milliseconds. This rapid processing happens before you're consciously aware of seeing anything. Your brain is already working on the image, already extracting information and making decisions. before the experience of seeing enters your conscious awareness. There's a lag, small but measurable, between when your brain processes something and when you become conscious of it. You live slightly in the past, experiencing events a fraction of a second after your brain has already responded to them. This is why athletes and musicians talk about entering flow states, where action seems to happen without thought. In those moments, they're not consciously deliberating each movement. They're allowing the faster, unconscious processing systems to operate without interference. Conscious thought, with its delays and deliberation, would actually slow them down. The fastest responses come from systems that bypass consciousness entirely. Your brain is constantly working beneath the surface of awareness, processing vast amounts of sensory information, making predictions, preparing responses, maintaining your body's functions. Consciousness is just the tip of the iceberg, the small portion of brain activity that rises into awareness. Beneath it, hidden from view, enormous amounts of processing occur every moment, keeping you alive, keeping you oriented, keeping you functional in a complex world that requires split-second responses. Deep underground, sealed away from the surface world for millions of years, are caves so isolated that they host ecosystems that evolved separately from the rest of Earth. These caves have no light, no connection to the outside world, no exchange of organisms with surface ecosystems. They've been cut off for so long that the creatures living in them have evolved in complete isolation, developing into species found nowhere else on the planet. Scientists discover new species every time they explore one of these isolated cave systems. Spiders, crustaceans, millipedes, fish, all adapted to life in perpetual darkness. Many of them blind, colorless, slow-moving, shaped by millions of years in an environment unlike anywhere else. The cave ecosystems often survive on chemosynthesis rather than photosynthesis. Instead of plants converting sunlight into energy, bacteria at the base of the food chain extract energy from chemical reactions, breaking down sulfur compounds, metabolizing methane, processing minerals in the water. These bacteria support entire food webs in the absence of any sunlight, any connection to the photosynthetic world that sustains most life on Earth. It's like finding alien ecosystems without leaving the planet. These caves show us that life can evolve in complete isolation, can adapt to extreme conditions, can find energy sources we don't normally think of as life-supporting. They're laboratories of evolution, running experiments in parallel to the rest of Earth's biosphere, producing solutions and adaptations we'd never predict. When we finally explore them carefully, minimizing contamination, we're stepping into worlds that have been separate from ours for longer than human history, longer than mammalian evolution, sometimes longer than the dinosaurs existed. We're discovering life that diverged from familiar forms millions of years ago and went its own way, adapting to darkness and isolation, creating beauty and strangeness in depths we're only beginning to understand. The speed of light is often described as constant, as the ultimate cosmic speed limit, unchanging throughout the universe. And in a vacuum, that's true. But light speed is actually quite variable depending on what it's traveling through. In a vacuum, light travels at 282 miles per second. The fastest speed possible, the speed limit built into the structure of space-time itself. But when light enters a medium like water, glass, or diamond, it slows down. In water, light travels at about 140,000 miles per second, 75% of its vacuum speed. In diamond, it slows to about 77,000 miles per second, less than half its maximum speed. This slowdown isn't because photons are getting tired or encountering friction. It's because the photons are being absorbed and re-emitted by atoms in the material. And this absorption-emission process takes time. The light appears to slow down because it's taking a longer path, constantly being captured and released by the material it's passing through. The actual photons, when they're traveling between atoms, still move at light speed, but the overall progress through the material is slower. This variable speed is why lenses work, why prisms split light into rainbows, why fiber optic cables can carry information. Light bends when it enters a new medium precisely because it changes speed, a phenomenon called refraction. Different wavelengths slow down by different amounts, which is why white light separates into colors when passing through a prism. Blue light slows more than red light, bending at a different angle. So the cosmic speed limit isn't quite as absolute as it first appears. Light is only at maximum speed in empty space. Everywhere else, it's slowed by interaction with matter, taking its time, moving at speeds that depend on what it's moving through. Even the fastest thing in the universe has to slow down sometimes, has to negotiate with the material world rather than simply passing through it untouched. Your skeleton feels permanent, solid, unchanging, the framework that's held you together since childhood, but it's actually in constant flux, continuously being torn down and rebuilt. Every 10 years or so, your entire skeleton is replaced. Specialized cells called osteoclasts dissolve old bone tissue, breaking down the minerals and protein matrix that give bones their strength. Other cells called osteoblasts build new bone in its place, depositing fresh calcium and collagen, maintaining the same structure while replacing all the material. It's like restoring an old building by replacing every brick while keeping the architectural design intact. This constant remodeling serves several purposes. It allows bones to respond to stress and load, becoming stronger where forces are greatest and lighter where less support is needed. It repairs microfractures that occur from everyday activity, preventing them from growing into serious breaks. It maintains mineral homeostasis, releasing calcium into the bloodstream when needed, and storing it when available. Your bones aren't just structural, they're metabolically active organs, participating in your body's chemistry. This is why osteoporosis is such a serious condition. It occurs when the balance between bone breakdown and bone building tips toward breakdown, when osteoclasts work faster than osteoblasts can rebuild. Bones become porous, weak, prone to fracture. It's not that the bones are staying the same and deteriorating. It's that the constant process of remodeling is occurring in an imbalanced way, removing more bone than is replaced. Your skeleton is dynamic, alive, responsive. It's been replaced multiple times over the course of your life, yet maintains the same basic shape, the same proportions, the same capacity to support and protect you. You're not held together by ancient framework. You're held together by tissues that are constantly dying and being reborn, maintaining your form through perpetual renewal rather than static permanence. There's a mathematical pattern that appears throughout nature with such regularity that it seems almost supernatural, the Fibonacci sequence. The sequence is simple. Start with 0 and 1, then each subsequent number is the sum of the previous two. So 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on, extending infinitely. It was described by Leonardo Fibonacci in 1202, but the pattern itself is far older, woven into nature long before humans noticed it. Flower petals often occur in Fibonacci numbers. Lilies have 3 petals, buttercups have 5, daisies have 34, 55, or 89. The spiral pattern of seeds in a sunflower head follows Fibonacci numbers, typically 21 spirals in one direction and 34 in the other, or 34 and 55, or 55 and 89, always consecutive Fibonacci numbers. Pine cones show the same pattern in their scales. Nautilus shells grow in logarithmic spirals that approximate the Fibonacci sequence. Hurricane cloud formations, galaxy spirals, the branching of trees, the arrangement of leaves on a stem. Fibonacci numbers appear again and again. Why? Because the sequence represents the most efficient way to pack growth in limited space. When plants arrange seeds or petals or branches according to this pattern, they maximize exposure to sunlight, minimize overlap, optimize resource distribution. The Fibonacci sequence emerges not because nature is following mathematical rules, but because the mathematics describes optimal solutions to physical problems. Evolution discovers these patterns through trial and error across millions of years, selecting for arrangements that work best. It's a glimpse of the deep relationship between mathematics and nature, a suggestion that mathematical patterns aren't arbitrary human inventions, but descriptions of actual structures in reality. The universe, it seems, has preferences, tendencies toward certain patterns that emerge independently in different contexts because they represent efficient solutions to common problems. Black holes have a reputation as cosmic vacuum cleaners, sucking up everything around them. But this is a misconception based on dramatic imagery rather than physics. A black hole doesn't suck any more than any other massive object. If the sun suddenly became a black hole with the same mass, which it can't, but imagine, Earth would continue its orbit exactly as before. Nothing would change gravitationally. We'd be plunged into cold darkness, yes, but we wouldn't be pulled inward. The gravitational pull depends on mass and distance, not on whether that mass is a star or a black hole. From Earth's orbital distance, the gravitational force would be identical. What makes black holes special isn't suction. It's the event horizon, the boundary beyond which escape becomes impossible. If you were to approach a black hole, you'd feel stronger and stronger gravitational pull as you got closer, just as you would approaching any massive object. But once you crossed the event horizon, even light moving at maximum speed couldn't escape. Not because the black hole is pulling harder, but because space-time itself is so curved that all paths lead inward. There's no outward direction anymore. Outside the event horizon, though, black holes behave like any other mass. If you were orbiting at a safe distance, you could maintain that orbit indefinitely. Satellites could circle a black hole just as they circle Earth. The danger comes from getting too close, from crossing that boundary where escape becomes impossible. But from a distance, a black hole is just a very compact, very dense mass, following the same gravitational laws as everything else. The misconception persists because black holes are dramatic, because the event horizon represents a point of no return that captures our imagination. But in reality, they're not cosmic monsters hunting for prey. They're just extremely dense objects whose gravity, like all gravity, follows predictable mathematical laws. They wait passively, affecting only what comes close enough to be trapped. Slime molds are among the strangest organisms on Earth. Neither plant, nor animal, nor fungus, but something altogether different. And despite having no brain, no nervous system, no centralized control whatsoever, they can solve complex problems. Scientists have tested slime molds by placing them in mazes with food at both ends. The slime mold, initially spreading throughout the maze, gradually retracts from dead ends and reinforces paths that lead to food, eventually finding the shortest route between the two food sources. It solves the maze without thought, without trial and error in the cognitive sense, simply through the distributed decision-making of its cellular network. Even more remarkably, researchers recreated a map of Tokyo with oat flakes representing urban centers and placed a slime mold at the location of Tokyo itself. The organism grew outward, connecting the food sources, and the network it created closely resembled Tokyo's actual rail system. Efficient, redundant, optimized for connecting all locations with minimal total distance. In some cases, the slime mold's solution was actually more efficient than what human engineers had designed. How does it do this without a brain? Through simple rules applied locally. Each part of the slime mold responds to chemical gradients, growing toward food, retracting from areas without resources, strengthening connections that prove useful. There's no central planning, no overview of the entire system. The intelligent behavior emerges from the aggregate of many simple decisions, from the interaction of parts following basic rules. It's a form of intelligence without consciousness, problem solving without thought, optimization through distributed processing. The slime mold reminds us that intelligence doesn't require brains, that complex solutions can emerge from simple rules, that nature has discovered multiple paths to adaptive behavior. Sometimes the most sophisticated solutions come from the simplest organisms. At the edge of our solar system, where the sun's influence begins to fade and interstellar space begins, there's a mystery that scientists haven't fully explained. The temperature there is warmer than it should be. According to our models of how the solar wind, the stream of charged particles flowing outward from the sun, should behave, the temperature should decrease steadily as these particles travel farther from their source, and it does decrease for much of the journey. But then, unexpectedly, it begins to rise again. The temperature at the boundary of our solar system, billions of miles from the sun, is higher than the temperature much closer in. Scientists call this the temperature anomaly, and despite decades of study, the mechanism remains unclear. Something is heating the solar wind as it approaches the heliopause, the boundary where the solar wind meets the interstellar medium. Perhaps it's turbulence in the plasma. Perhaps it's interactions with magnetic fields. Perhaps it's energy from shock waves created when the solar wind slows down. The truth is, we don't fully know. The Voyager spacecraft, having crossed into interstellar space, have sent back data about this region, but mysteries remain. The boundary between our solar system and the galaxy beyond is more complex, more dynamic than we expected. It's not a simple transition from solar to interstellar. It's a region of interaction, of complex physics, of phenomena we're still working to understand. It's humbling to realize that even at the edge of our own solar system, in a region we've actually visited with spacecraft, there are fundamental questions we can't yet answer. The universe maintains its mysteries even in our own cosmic neighborhood, reminding us how much remains to be discovered, how many phenomena still challenge our understanding. Your memories feel like recordings, like files stored in specific locations in your brain that you can retrieve when needed. But that's not how memory works at all. Memories aren't stored in single locations. They're distributed across networks of neurons throughout your brain, encoded in the patterns of connections between cells. When you remember something, your brain is reconstructing that memory from pieces, fragments of sensory information, emotional context, related associations, all woven together in real time. You're not retrieving a recording. You're recreating the memory each time, rebuilding it from components. This is why memories change over time. Each time you recall a memory, you're reconstructing it. And that reconstruction can be influenced by your current mood, by new information you've learned since, by other memories that have similar elements. The memory gets updated, slightly altered, then stored again in its modified form. You're not remembering the original event. You're remembering the last time you remembered it, which was based on the time before that, and so on, back through a chain of reconstructions. This makes memory fallible in ways we don't like to admit. Eyewitness testimony, which feels so certain, so clear, can be completely wrong because memories are susceptible to suggestion, to leading questions, to the incorporation of information learned after the event. You can remember things that never happened, or remember events differently from how they occurred, and feel absolutely certain that your memory is accurate. But this system also has advantages. Distributed memory is robust. Damage to one area doesn't erase specific memories because they're stored across multiple locations. And the reconstructive nature allows us to extract meaning, to see patterns, to learn from experiences rather than just recording them. Memory isn't a camera. It's an interpretive system, constantly updating, constantly learning, trading perfect accuracy for flexibility and meaning. The platypus is so strange, so improbable, that when European scientists first encountered preserved specimens, they assumed it was a hoax, a duck's bill sewn onto a beaver's body by a mischievous taxidermist. But it's real, and it's genuinely bizarre. The platypus is one of only 5 species of monotremes, mammals that lay eggs instead of giving birth to live young. It has a bill like a duck, but it's actually a highly sensitive sensory organ covered in electroreceptors. The platypus hunts with its eyes, ears, and nostrils closed, detecting the tiny electrical fields produced by muscle contractions in its prey. It's one of the few mammals capable of electroreception, using this sense to navigate and hunt in murky water. Male platypuses have venomous spurs on their hind legs. Yes, venomous mammals exist that can deliver a painful sting used during mating competition. They have dense fur that traps air for insulation, webbed feet for swimming, and they nurse their young despite having no nipples. Milk simply seeps through pores in the skin for the babies to lap up. They're a mosaic of features that seem borrowed from different animal groups, assembled in a combination that shouldn't work but does. The platypus represents an ancient lineage, a mammal that diverged from other mammals about 166 million years ago, long before most modern mammal groups emerged. It's essentially a living fossil, preserving characteristics that were present in early mammals: the egg-laying, the reptilian gait, the sprawling limbs. It's a window into what mammals were like before they became fully mammalian, in the way we typically understand the term. Evolution doesn't always move toward increasing complexity or specialization. Sometimes it preserves ancient forms, allows them to persist alongside more advanced relatives, creating living examples of evolutionary stages long past. The platypus is one of nature's peculiar gifts, a reminder that life's history is full of branches that never went extinct, lineages that found their niche and held on through hundreds of millions of years of change. Beneath your feet, if you could journey downward through thousands of miles of rock and metal, you'd eventually reach the Earth's core. And at the center, at the innermost part of our planet, temperatures rival the surface of the sun. The inner core reaches temperatures of about 10,800 degree Kelvin, around 6,000 degree Kelvin. That's as hot as the sun's photosphere, the visible surface from which light and heat radiate into space. It seems impossible that such heat could exist inside our planet, that we're standing on the relatively cool crust of a world whose heart burns at stellar temperatures. Yet this is the reality, confirmed through seismology, through studying how earthquake waves travel through Earth's interior. The heat comes from two primary sources. First, there's primordial heat, energy left over from Earth's formation 4.5 billion years ago. When dust and rock collapsed together to form our planet, that kinetic energy converted to heat, and the planet has been slowly cooling ever since. But it's cooling very slowly, insulated by thousands of miles of rock, maintaining much of its original heat. Second, there's heat from radioactive decay. Elements like uranium, thorium, and potassium in Earth's interior undergo radioactive decay, breaking down into lighter elements and releasing energy in the process. This has been happening continuously for billions of years, adding heat to the planet's interior, helping to maintain the high temperatures that drive plate tectonics, volcanism, and the generation of Earth's magnetic field. The inner core is solid despite these temperatures because the pressure is so immense, over 3.6 million times atmospheric pressure at sea level, that iron cannot melt. It's squeezed into a solid state by the weight of the entire planet pressing inward. The outer core, at slightly lower pressure, remains liquid, and its motion generates the magnetic field that protects us from solar radiation. We live on a thin shell wrapped around a molten interior, above a solid metal core as hot as the sun. In 2012, physicists created something that seems to violate the laws of thermodynamics, something that appears to get something from nothing: time crystals. Normal crystals have structures that repeat in space. Table salt, for example, has sodium and chlorine atoms arranged in a regular, repeating lattice. Time crystals have structures that repeat in time. They oscillate, moving through different states in a regular pattern, but they do so without using energy. They're in their ground state, their lowest energy configuration, yet they're still moving, still changing, perpetually. This seems impossible. One of the fundamental principles of physics is that perpetual motion machines can't exist, that you can't have motion without energy expenditure, that everything eventually reaches equilibrium and stops. Time crystals appear to violate this, oscillating forever without energy input, like a clock that runs eternally without being wound. The resolution to this apparent paradox involves quantum mechanics and symmetry breaking. Time crystals exist in states where time translation symmetry is broken, meaning their properties change predictably over time, even in their lowest energy state. They're not violating conservation of energy, but they are demonstrating behavior that classical physics would forbid. Behavior that only becomes possible in the quantum realm. Time crystals were first proposed theoretically in 2012 and experimentally demonstrated in 2016. They're not just curiosities. They might have practical applications in quantum computing, where maintaining quantum states for long periods is crucial. They represent states of matter that we didn't know were possible. Patterns that exist not in space but in time, oscillations without energy cost. The universe continues to surprise us with possibilities we didn't imagine, with states of matter that seem to bend the rules, with solutions to equations we thought were impossible. Time crystals are one more reminder that reality is stranger, more subtle, more full of loopholes and edge cases than our intuitions suggest. Voyager 1 is the most distant human-made object, launched in 1977 to explore the outer planets, and now traveling through interstellar space more than 15 billion miles from Earth. It's so far away that its radio signals, traveling at the speed of light, take over 22 hours to reach us. When we send a command to Voyager, we wait 22 hours for the signal to arrive, then another 22 hours for confirmation to return. A 44-hour round-trip conversation with a spacecraft built in the 1970s, still functioning, still sending data from beyond the solar system. The signal is incredibly weak. By the time it reaches Earth, it carries less power than a snowflake hitting the ground, about 0.1 billion billionths of a watt. Yet we can still detect it, still decode it, still extract meaningful information from this whisper across the void. The spacecraft's 23-watt transmitter, weaker than a refrigerator light bulb, reaches across billions of miles because we've built receivers sensitive enough to hear it. Voyager carries a golden record, a phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. It includes greetings in 55 languages, music from various cultures, natural sounds like thunder and whale songs, and 116 images. It's a message in a bottle, tossed into the cosmic ocean, unlikely ever to be found, but carrying the hope that someday, somehow, someone else might hear humanity's greeting. The spacecraft is powered by plutonium-238, which generates heat through radioactive decay. That heat is converted to electricity to run the instruments and transmitter, but the plutonium is slowly depleting, the power output gradually declining. By the mid-2020s, engineers will have to start shutting down instruments to conserve power. By 2036 or so, Voyager will go silent, continuing its journey through the galaxy with no one listening, carrying its golden record into the eternal night. Life is resilient, but some forms push that resilience to extremes that seem to defy what life can mean. Certain bacteria can survive in dormant spores for 25 million years or more, longer than humans have existed as a species, longer than most mammal species persist in the fossil record, longer than the asteroid impact that killed the dinosaurs. These spores contain all the genetic material and cellular machinery needed for life, but they're not active. They're not metabolizing, not growing, not reproducing. They're waiting. Scientists have revived bacteria from amber, fossilized tree resin. That was 40 million years old. They've cultured bacteria from salt crystals buried for tens of millions of years. When given water and nutrients, these ancient organisms spring back to life, begin reproducing, resume all the activities that define living things. They're not just preserved like fossils, they're dormant, suspended, capable of reanimation after epochs of geological time. How is this possible? The spores are incredibly tough, with multiple layers of protection around the genetic material. DNA is tightly packed and stabilized. Metabolic processes are completely shut down, eliminating the chemical reactions that would normally cause gradual deterioration. The spores enter a state where time essentially stops for them biologically. They're not aging, not changing, just waiting for conditions that might allow them to resume life. This has profound implications. It means that life, once established, is extraordinarily difficult to eliminate completely. Sterilizing environments is far harder than we thought, and it raises questions about panspermia, the possibility that life could travel between planets or even star systems, riding on asteroids or comets, waiting in dormancy for millions of years until landing somewhere with suitable conditions. Life might not need to evolve independently on every planet. It might spread patiently across the cosmos, waiting for opportunities to awaken. The Mandelbrot set is a mathematical object with a peculiar property. It contains infinite complexity generated from a remarkably simple rule. The rule is straightforward. Take a complex number, square it, add the original number, then repeat with the result. Keep doing this iteration. If the numbers stay bounded, don't fly off to infinity, the original number is part of the Mandelbrot set. If they explode toward infinity, it's not. That's the entire rule. Simple enough to explain in a sentence. Yet when you plot the Mandelbrot set visually, you get an object of stunning, infinite detail. The boundary of the set is fractal. It has structure at every scale. You can zoom in forever and always find new patterns, new spirals, new shapes resembling the whole. The complexity never ends. You could spend eternity zooming deeper and never reach a point where the detail disappears, where you find smoothness or simplicity. This suggests something profound about the relationship between simplicity and complexity. The Mandelbrot set shows that incredibly simple rules can generate infinite complexity. You don't need complicated equations, elaborate systems, or vast amounts of information to create endless detail. Sometimes a single simple rule, applied recursively, unfolds into something inexhaustibly complex. This has implications beyond mathematics. It suggests that the complexity we see in nature, in coastlines, in weather patterns, in biological systems, might emerge from relatively simple underlying rules. That complexity doesn't necessarily require complex causes. That elaboration can arise from iteration, from feedback, from simple processes building on themselves across time or scale. The Mandelbrot set is beautiful partly because it's unexpected, because our intuitions tell us that simple things should be simple all the way down, that complexity requires complex origins. But mathematics shows us otherwise, reveals that the boundary between simplicity and complexity is permeable, that one can generate the other, that infinity can hide inside finitude, waiting to be discovered. Gravity isn't what you think it is. Newton described it as a force pulling objects together, and that description works well enough for everyday purposes. But Einstein showed us something stranger, more fundamental. Gravity isn't a force at all. According to general relativity, gravity is the curvature of space-time itself. Massive objects like Earth or the Sun don't pull on you. They bend the fabric of space and time around them, and you're simply following the straightest possible path through that curved geometry. You're not falling toward Earth because it's pulling you. You're traveling in what physicists call a geodesic, a straight line through curved space-time, and the ground is accelerating upward to meet you, constantly pushing against your natural motion. This sounds absurd until you realize it explains things Newton's gravity couldn't. It explains why all objects fall at the same rate regardless of mass, because they're all following the same curved space-time geometry. It explains why light bends near massive objects even though light has no mass for gravity to pull on, because light follows curved space-time too. It explains the precession of Mercury's orbit, the gravitational lensing of distant galaxies, the existence of black holes. When you're standing still on Earth's surface, you're actually accelerating upward at 9.8 meters per second squared, held in place by the ground, pushing up against you, preventing you from following your natural geodesic path through space-time. In orbit, astronauts aren't experiencing zero gravity. They're in free fall, following their natural path through curved space-time without obstruction. They're weightless because nothing is pushing against them, not because gravity has disappeared. Space-time is a dynamic thing, a fabric that bends and flexes in response to mass and energy, and we move through it following paths determined by that curvature. Gravity is geometry. Mass tells space-time how to curve, and space-time tells mass how to move. It's a dance between matter and the structure of reality itself. Your brain contains approximately 86 billion neurons. Each neuron can form connections, synapses, with thousands of other neurons. The number of possible patterns of connections in your brain exceeds the number of atoms in the observable universe. Let that settle for a moment. The atoms in the entire visible cosmos, every star, every planet, every particle of gas floating in intergalactic space, number around 1080, a 1 followed by 80 zeros. The number of possible neural connection patterns in your brain is far, far larger. Some estimates put it at 10 1,000,000 or higher, numbers so vast they lose meaning, numbers that exceed our ability to conceptualize. This astronomical connectivity is what makes consciousness, memory, thought possible. Each pattern of neural connections represents a potential state of mind, a possible configuration of thoughts and memories and perceptions. Your brain doesn't just have one pattern, it's constantly shifting between patterns, reconfiguring connections, forming new associations, strengthening some pathways while others weaken. Every experience you have, every thought you think, every memory you form is encoded in these patterns. Learning something new means creating or strengthening certain connections. Forgetting means connections weakening or dissolving. Your personality, your knowledge, your skills, your fears and hopes and dreams, all of it exists as patterns of connectivity among these 86 billion neurons, as particular configurations within the space of nearly infinite possibility. And yet, for all this complexity, the basic components are simple. Neurons are just cells that pass electrical and chemical signals. The brain is meat, chemistry, electricity. But organized in this particular way, connected in these patterns, it becomes something more. It becomes you. A pattern of connectivity so complex it achieves self-awareness, so intricate it can contemplate its own existence, so vast it contains more potential configurations than there are atoms in the cosmos. Antimatter sounds like science fiction, but it's real, and it's being produced around you all the time, though it exists only briefly before annihilating. For every type of particle that exists, electrons, protons, neutrons, there's an antimatter counterpart with opposite charge, but otherwise identical properties. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy with perfect efficiency according to EMC2. This isn't burning or chemical reaction. It's total conversion, releasing more energy per unit mass than any other process in nature. Positrons, the antimatter version of electrons, are produced regularly in medical PET scans. That's what the P stands for, positron emission tomography. Radioactive isotopes injected into patients emit positrons, which immediately collide with electrons in the body, annihilating and producing gamma rays that the scanner detects. Cosmic rays hitting the upper atmosphere create antimatter particles. Particle accelerators produce them routinely for research. But storing antimatter is extraordinarily difficult. It can't touch ordinary matter without annihilating, so it must be suspended in electromagnetic fields in high vacuum, isolated from any physical container. Even air molecules would cause annihilation. Scientists have managed to trap antimatter atoms for several minutes, a remarkable achievement given the challenges involved. Here's the deep mystery. The Big Bang should have created equal amounts of matter and antimatter. They should have annihilated each other completely, leaving only energy. The universe should be empty of both matter and antimatter, just pure radiation. But obviously that didn't happen. Somehow there was a tiny asymmetry, a slight excess of matter over antimatter, about one extra matter particle for every billion matter-antimatter pairs. That slight imbalance is why anything exists at all, why stars and planets, and you can be here. We don't fully understand why that asymmetry occurred, what caused matter to win out. It's one of the deepest unsolved problems in physics. The butterfly effect is real. It's not just a metaphor or poetic exaggeration. It's a mathematical property of certain systems called sensitive dependence on initial conditions. In the 1960s, meteorologist Edward Lorenz was running weather simulations on an early computer. He decided to rerun a simulation from the middle, typing in the numbers the computer had calculated earlier. But he rounded them slightly, entering 0.506 instead of 0.506127, a difference of about 1 part in 1,000. He expected to see the same weather pattern emerge. Instead, the simulation diverged dramatically, producing completely different weather within weeks of simulated time. This tiny change, smaller than any measurement error, smaller than any real uncertainty in atmospheric conditions, led to radically different outcomes. Lorenz realized that weather is chaotic in the technical sense. Small changes amplify exponentially over time through feedback loops and non-linear interactions. He famously asked whether a butterfly flapping its wings in Brazil could set off a tornado in Texas. Not that it would cause the tornado directly, but that its tiny disturbance could amplify through the system, eventually making the difference between a tornado forming or not. This has profound implications. It means long-term weather prediction is fundamentally impossible, not just practically difficult. No matter how many sensors we deploy, how powerful our computers become, we can never measure initial conditions perfectly enough to predict weather more than a few weeks out. The uncertainty inherent in any measurement, however small, grows exponentially until it overwhelms the prediction. Chaos isn't randomness. These systems are deterministic, following precise rules, but they're unpredictable because tiny uncertainties, inevitable in any real measurement, grow until they dominate the outcome. Weather, ecosystems, the stock market, even the orbits of planets over long time scales, all show chaotic behavior. The universe contains systems where the tiniest perturbation cascades into vastly different futures, where determinism and unpredictability coexist, where knowing the rules isn't enough to predict the outcome. Most of the universe is missing, not metaphorically, literally. About 95% of everything that exists is made of substances we've never directly detected, that we know almost nothing about. We call them dark matter and dark energy, names that reveal our ignorance. Dark matter makes up about 27% of the universe's mass energy. We know it exists because we can see its gravitational effects. Galaxies rotate too fast for the visible matter they contain. They should fly apart unless there's additional invisible mass holding them together. Galaxy clusters bend light from objects behind them more than their visible mass would predict. Something is there, exerting gravity, but not emitting or absorbing light. It's invisible to all our telescopes, detectable only through its gravitational influence. Dark energy is even more mysterious, comprising about 68% of the universe. It's a form of energy that fills space itself, causing the expansion of the universe to accelerate. Empty space isn't actually empty. It has energy, and that energy pushes space apart, driving galaxies away from each other faster and faster. We discovered dark energy in 1998 by measuring distant supernovae and finding that the universe's expansion is speeding up rather than slowing down as gravity should cause it to. So ordinary matter, everything we can see, everything made of atoms, everything in the periodic table, everything we've ever directly studied, accounts for only about 5% of the universe. We're a tiny minority, living in a cosmos dominated by substances we can't see, can't touch, can't directly detect, that we know exist only through their gravitational effects and their influence on cosmic expansion. It's humbling and exciting. Humbling because we've been studying the universe for centuries, and only recently realized we've been missing 95% of it. Exciting because it means there are entire categories of phenomena waiting to be discovered. Fundamental aspects of reality we haven't even begun to understand. The universe is far stranger and more complex than it appears, and we're still in the early stages of figuring it out. The concept of now seems obvious, universal. Right now is happening everywhere simultaneously, a cosmic present moment shared across the universe. Except it isn't. There is no universal now. Einstein's relativity shows that simultaneity is relative. What counts as now depends on your motion and position. Events that appear simultaneous to you might occur in different orders for someone moving at a different velocity. There's no absolute time, no cosmic clock ticking away the same seconds everywhere. Time itself is flexible, local, observer-dependent. Imagine two events happening in distant locations, a supernova in one galaxy and a planet forming in another. You, from your position and state of motion, might measure these as simultaneous, but someone traveling at high speed relative to you would measure them as happening at different times, one before the other, and both measurements are equally valid. There's no fact of the matter about which event happened first. The order depends on the observer. This isn't just about perception or measurement limitations. It's fundamental to how reality works. Space and time are woven together into space-time, and how that four-dimensional fabric divides into space and time depends on your motion. What's simultaneous for you is a diagonal slice through space-time from your perspective. But someone moving differently takes a different slice, defines simultaneity differently. The practical effects are tiny at everyday speeds. Your now and your friend's now across town are essentially the same. But at high speeds or across cosmic distances, the disagreement becomes significant. There's no privileged frame of reference, no absolute time ordering events throughout the universe. Past, present, and future are less absolute than they seem, more fluid, more dependent on perspective. The universe doesn't have a single present moment. It has countless present moments, all equally valid, all slightly different, depending on who's measuring and how they're moving. Scale is relative, and you exist at a peculiar midpoint in the universe's hierarchy of sizes. The ratio of your size to the size of an atom is roughly equal to the ratio of your size to the sun's diameter. You're geometrically positioned midway between the quantum realm and stellar scales. You're as much larger than an atom as the sun is larger than you. This isn't coincidence. It's a consequence of the forces that govern matter at different scales, and the particular way those forces allow complex structures to form. Going smaller, a typical atom is about 10 torr to 10 meters across. You're about 10 1 meters, between 1 and 2 meters tall. Going larger, the sun is about 10 more 9 meters in diameter. Each step is roughly 9 orders of magnitude, a billion-fold increase in scale. You're balanced in the middle, larger than atoms, by the same factor that makes the sun larger than you. This means looking inward toward the quantum realm is as vast a journey as looking outward toward stars. The microscopic world is as far below us as the astronomical world is above us. We exist at the geometric mean, experiencing both the quantum and the cosmic as equally distant, equally alien, equally difficult to access directly. Perhaps this is why we're conscious observers, We're at the scale where complexity can emerge. Too small and quantum effects dominate, preventing the stable structures needed for information processing. Too large and gravitational collapse becomes inevitable. Consciousness might require a particular range of scales, a Goldilocks zone where atoms can form molecules, molecules can form cells, cells can form brains, and brains can achieve the information density needed for thought. We're not just observers in the universe. We're observers of a particular scale, positioned at a natural midpoint where the universe can reflect on itself. Mushrooms appear to be plants. They grow in soil, remain stationary, seem passive, but they're more closely related to animals than to plants, an evolutionary kinship that reveals how arbitrary our categories can be. Both animals and fungi evolved from the same ancient ancestor, a single-celled organism that existed perhaps 1.5 billion years ago. Plants branched off much earlier, taking a different evolutionary path. The genetic and biochemical evidence is clear. You share more recent common ancestry with mushrooms than mushrooms do with trees. Both fungi and animals are heterotrophs. We consume organic matter rather than producing it through photosynthesis. Both store energy as glycogen rather than starch. Both have cell walls containing chitin, the same substance that makes insect exoskeletons and lobster shells. At the molecular level, at the level of cellular machinery, fungi and animals are siblings, while plants are more distant cousins. Fungi occupy a strange ecological niche. They're decomposers primarily, breaking down dead organic matter and recycling nutrients back into ecosystems. But they do this by secreting digestive enzymes outside their bodies, essentially digesting their food externally, then absorbing the results. They're like animals turned inside out, externalizing the digestive process we keep internal. And the mushroom you see is just the fruiting body, the reproductive structure. The actual organism is underground, a network of thread-like hyphae called mycelium, spreading through soil, sometimes across acres, sometimes weighing tons. The largest living organism on Earth is a fungus in Oregon, a honey mushroom whose mycelium covers over 2,000 acres and might be thousands of years old. What we think of as separate mushrooms are just the reproductive structures of the single vast organism beneath the surface. Quantum mechanics contains a principle that seems almost philosophical, yet it's experimentally verified, mathematically rigorous, fundamental to reality, the Heisenberg uncertainty principle. You cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you measure one, the less precisely you can know the other. This isn't a limitation of measurement technology. It's not that we lack sufficiently sensitive instruments. It's that the properties themselves don't have definite values simultaneously. A particle doesn't have both a precise position and a precise momentum. It has one or the other or neither, but not both at once. This emerges from the wave nature of matter. At quantum scales, particles are described by wave functions, probability distributions that spread over space. A wave localized at one position requires many different frequencies, many different momentums to construct. A wave with a single definite momentum is spread throughout space, having no specific position. Position and momentum are complementary properties, related by a fundamental trade-off built into the mathematics of waves. Werner Heisenberg discovered this in 1927, and it's been confirmed countless times since. You can measure position precisely, but then momentum becomes uncertain. You can measure momentum precisely, but then position becomes uncertain. The product of the uncertainties has a minimum value. You can't compress both uncertainties below a certain threshold. Nature enforces this limit absolutely. This has profound implications. It means the quantum world is fundamentally probabilistic, not deterministic. Particles don't have definite properties until measured. They exist in superpositions, probability clouds that collapse only when observed. The universe at its smallest scales is fuzzy, indefinite, existing in a state of potentiality rather than actuality. It's not that we don't know where a particle is. It's that the particle doesn't have a definite location until something forces it to choose one through measurement. Quantum tunneling is one of those phenomena that sounds impossible, but enables much of modern technology and powers the sun itself. Classical physics says that objects need sufficient energy to overcome barriers. A ball can't roll over a hill unless it has enough energy to reach the top. But in quantum mechanics, particles can tunnel through barriers they don't have energy to surmount. They disappear on one side and reappear on the other, without passing through the space between. This happens because particles aren't really particles. They're waves, probability distributions. A wave encountering a barrier doesn't stop abruptly at the boundary. It decays exponentially inside the barrier. But if the barrier is thin enough, some of the wave function extends through to the other side. There's a non-zero probability of finding the particle beyond the barrier, and quantum mechanics says that probability sometimes manifests as reality. The particle tunnels through. This isn't rare. It's happening constantly. Nuclear fusion in the sun's core requires quantum tunneling. Hydrogen nuclei don't have enough energy to overcome their electromagnetic repulsion through classical means. But they tunnel through the repulsive barrier, fuse and release energy. Without tunneling, the sun wouldn't shine. Stars wouldn't exist. The universe would be dark and cold. Scanning tunneling microscopes use this effect to image individual atoms. Electrons tunnel between a sharp probe tip and a surface, creating a current proportional to the distance. By scanning the tip across a surface and measuring tunneling current, scientists can map atomic scale features. The first transistors relied on tunneling. Modern electronics uses tunnel diodes. Quantum computers exploit tunneling to perform calculations. Reality at the quantum level is less solid than it appears. Barriers aren't absolute. Particles can be in two places at once, can pass through walls, can exist in states of superposition that defy classical logic. And these impossible-seeming phenomena aren't just theoretical curiosities. They're essential to how the universe actually works, how stars burn, how electronics function, how life itself is possible. The observable universe is 93 billion light-years across, but the universe is only 13.8 billion years old. Light has only had 13.8 billion years to travel. So how can the observable universe be larger than the distance light could have traveled? The answer is expansion. Space itself has been expanding since the Big Bang, and crucially, space can expand faster than light can travel through it. This doesn't violate relativity. Nothing is moving through space faster than light, but space itself can stretch at any rate. Objects that were close together when light was emitted have moved apart during the light's journey, carried by expanding space. In the early universe, there was a period called cosmic inflation when space expanded exponentially, faster than light, stretching the universe from subatomic to cosmic scales in a fraction of a second. This means objects we see now, whose light took 13 billion years to reach us, are currently much farther away than 13 billion light years, because space has continued expanding during that light's journey. Think of it like this. Imagine drawing dots on a deflating balloon, then inflating it. The dots move apart, not because they're traveling across the rubber, but because the rubber itself is stretching. Galaxies aren't moving away from us through space. Space is expanding, carrying them with it. And in the farthest reaches, space is expanding so fast that light from those regions will never reach us. They're receding faster than light can approach us. This means the observable universe, the region from which light has had time to reach us, is just a fraction of the total universe. Beyond the cosmic horizon, there's more universe we can never see, will never see, regions that are causally disconnected from us forever because the expansion carries them away faster than light can bridge the gap. The universe is larger than what's observable, possibly infinite, definitely vaster than we can ever access. Your brain can't multitask. This feels wrong because we multitask constantly, listening to music while reading, walking while talking, checking email during meetings. But neuroscience reveals these are illusions of simultaneity. What your brain actually does is task switching, rapidly alternating attention between activities so quickly it feels simultaneous. When you think you're doing two things at once, you're actually switching between them multiple times per second, giving each a slice of attention before moving to the other. This creates the subjective experience of multitasking, but it comes with costs. Every switch requires time and cognitive resources. Your brain has to disengage from one task, shift attention, engage with the new task, and reload relevant information. These switches might take only hundreds of milliseconds each, but they accumulate. Studies show that people who frequently multitask perform worse at both tasks than people who focus on one thing at a time. The switching overhead reduces efficiency, increases errors, impairs memory formation. Some activities can genuinely occur simultaneously if they use different neural systems. You can walk and talk because walking becomes automatic, handled by motor control systems that don't require conscious attention. But two tasks requiring the same type of attention, reading email while listening to a presentation, necessarily compete for resources. One always suffers while you're attending to the other. This is why driving while texting is so dangerous. Both tasks require similar types of attention: visual processing, decision-making, response selection. Your brain literally cannot process both simultaneously, so it switches between them. And during those moments when attention is on the phone, the driving task is effectively paused. You might miss critical information, fail to notice changing conditions, respond slowly to hazards. Focused attention isn't just more efficient, it's how your brain is designed to work optimally. The feeling that you can multitask task successfully is largely an illusion, a misperception of your own cognitive processes. Your brain is an incredible organ, but it has limits, and one of those limits is the inability to give full attention to multiple demanding tasks simultaneously. Water has memory, though not in the mystical sense sometimes claimed. Its molecular structure can be influenced by its history, and this affects its physical properties in measurable ways. When water freezes, the arrangement of molecules in ice crystals depends partly on how the water was cooled and what it encountered during cooling. Water that has been frozen and melted retains microscopic ice nucleation sites, tiny imperfections or dissolved particles that served as starting points for ice formation. When this water freezes again, it often freezes more readily, at slightly higher temperatures, because these nucleation sites are still present, even in liquid water. The hydrogen bonds between water molecules constantly form and break, creating transient networks and structures that persist for picoseconds before dissolving. The history of these structures, what the water has dissolved, what surfaces it has contacted, how it's been agitated, influences the statistical distribution of current structures. Water remembers in the sense that its recent history affects its current state. This isn't pseudoscience about water retaining information about dissolved substances after they're removed. That's homeopathy, and it has no scientific support. But there is real physics here. Water's properties are history-dependent at the molecular level. The way water flows through pipes, how readily it boils or freezes, even how it tastes, can be influenced by its past interactions with minerals, temperature changes, and physical agitation. Ice itself comes in at least 18 different crystalline forms, depending on temperature and pressure during formation. Each form has different properties, different molecular arrangements. Water can transition between these forms, and the path it takes through these transitions affects which form ultimately appears. History matters. Past states influence present behavior. Water is more complex than it appears. This simple molecule, just 2 hydrogen atoms and an oxygen, exhibits behaviors that still challenge complete understanding. Its phase diagram is complicated. Its anomalous density maximum at 4 degrees C defies normal liquid behavior. It's both common and strange, familiar and mysterious, simple in composition, yet complex in behavior. The placebo effect is so powerful that it works even when you know you're taking a placebo, which challenges everything we thought we understood about it. For decades, researchers assumed placebos worked through deception. Patients improved because they believed they were receiving real treatment. The expectation itself triggered real physiological changes: reduced pain, improved mood, decreased inflammation, even measurable changes in brain activity and neurotransmitter levels. The mind's expectations were altering the body's chemistry. But recent studies have shown something stranger. Patients given pills labeled as placebos told explicitly that the pills contain no active ingredients, still show improvement compared to patients receiving no treatment at all. Open-label placebos work. The knowledge that you're taking a fake treatment doesn't eliminate its benefit. How is this possible? The mechanisms aren't fully understood, but they seem to involve conditioning and ritual. The act of taking medication, the daily routine, the association with treatment, the clinical context, triggers learned, responses even when you know intellectually that the pill is inert. Your body has learned to associate pill taking with healing, and that association activates physiological responses, independent of belief about the pill's contents. This reveals how deeply intertwined mind and body actually are. Your brain's expectations, your learned associations, your engagement in healing rituals, all of these produce tangible biochemical effects. Neurotransmitter levels change, pain perception alters, immune function modulates. These aren't imaginary improvements, they're measurable, objective changes in physiology triggered by psychological factors. The implications are profound. It means context matters in medicine. How treatments are delivered, the patient-doctor relationship, the rituals surrounding care, all of these influence outcomes through placebo mechanisms. It doesn't mean we don't need real medicines, but it does mean that healing is more than just biochemistry. The mind's influence on the body is real, measurable, and powerful enough to produce clinical benefits even when we know we're being tricked. The game of Go, an ancient board game invented in China thousands of years ago, contains more possible positions than there are atoms in the observable universe. Go is played on a 19x19 grid with black and white stones. Players alternate placing stones, trying to control territory. The rules are simple, simpler than chess in many ways, but the complexity that emerges is staggering. After just a few moves, the number of possible board positions explodes exponentially. Mathematicians estimate there are approximately 10^170 legal board positions in Go. The observable universe contains about 1080 atoms. Go's possibility space exceeds the physical universe by a factor of 1090. That's a trillion times more Go positions than atoms in existence. This is why Go was considered the holy grail for artificial intelligence. Chess was conquered by computers in 1997, but Go remained beyond AI capabilities for nearly 2 more decades. The number of positions is too vast for brute force calculation. Chess computers could evaluate positions deeply through calculation because the possibility tree, while large, was searchable. Go required intuition, pattern recognition, strategic understanding that seemed uniquely human. When AlphaGo defeated the world champion in 2016, it did so not through brute force, but through neural networks trained on millions of games, learning to recognize patterns and evaluate positions intuitively rather than calculating exhaustively. It was a milestone in AI development, the creation of machines that could handle problems too vast for calculation, that could develop something resembling intuition. The complexity hidden in Go's simple rules reminds us that richness doesn't require complication. 19 by 19 intersections, 2 colors of stones, a handful of rules, and from this minimal foundation emerges a game so complex that it contains more possibilities than physical reality itself. Simplicity and complexity aren't opposites. Sometimes one generates the other. Sometimes the deepest complexity emerges from the simplest foundations. Gravitational waves pass through Earth constantly, dozens of times per day, ripples in the fabric of space-time itself, created by cataclysmic events billions of light years away. When massive objects accelerate, particularly when black holes or neutron stars orbit each other and merge. They create disturbances in space-time that propagate outward at the speed of light. These waves stretch and compress space itself as they pass, altering distances by tiny amounts. When they pass through Earth, they stretch it in one direction while compressing it in the perpendicular direction, then reverse, oscillating as the wave passes through. The distortions are incredibly small. A gravitational wave from colliding black holes billions of light years away might change the distance between two objects by less than the width of a proton over a distance of several kilometers. Detecting such tiny changes requires instruments of extraordinary precision. The LIGO detectors that first detected gravitational waves in 2015 are among the most sensitive measuring devices ever built. Einstein predicted gravitational waves in 1916 as a consequence of general relativity, but he doubted they could ever be detected. They were too weak, too subtle. For a century, they remained theoretical, a prediction that couldn't be tested. Then in 2015, LIGO detected the merger of two black holes 1.3 billion light-years away, confirming Einstein's century-old prediction and opening a new way of observing the universe. Gravitational wave astronomy lets us detect events invisible to traditional telescopes. Black hole mergers produce no light, but they create powerful gravitational waves. Neutron star collisions produce both light and gravitational waves, and observing both simultaneously gives unprecedented insight into these events. We're now able to sense cosmic violence through space-time itself, feeling the geometry of reality flex and ripple as massive objects collide in the distant universe. The waves pass through everything, planets, stars, galaxies, without being absorbed or scattered. Right now, as you rest there, space-time around you is oscillating slightly as gravitational waves from distant cosmic catastrophes pass through. You're too large to notice the effect, and it's far too subtle to affect you, but it's happening. Reality itself is vibrating with the echoes of colliding black holes, and we've finally learned to listen. The observer effect in quantum mechanics is often misunderstood as consciousness affecting reality. But the truth is stranger and more subtle than that. In quantum mechanics, particles exist in superpositions. They don't have definite properties until measured. Electron doesn't have a definite position. It has a wave function describing probabilities of finding it in various locations. But when you measure the electron's position, the wave function collapses, and the electron is found at one specific location. The act of measurement fundamentally changes the system. This isn't because consciousness is magical, or because the universe cares whether anyone is watching. It's because measurement requires interaction. To measure something, you must interact with it, bounce photons off it, pass it through a field, register it with a detector. These interactions inevitably disturb the quantum system, forcing it out of superposition into a definite state. You can't measure position without affecting momentum, can't detect a particle without interacting with it in ways that change it. The observer in the observer effect doesn't need to be conscious. A photographic plate observes. A detector observes. Any interaction that causes decoherence, the destruction of quantum superposition through environmental interaction, constitutes observation. Consciousness isn't required. What's required is physical interaction that entangles the quantum system with something else, making the superposition choose a definite state. This has profound implications. It means the properties of quantum systems aren't pre-existing, but emerge through measurement. Before measurement, particles don't have hidden definite values. We simply don't know. They genuinely exist in states of superposition, being multiple possibilities simultaneously. Reality at the quantum level is indeterminate, probabilistic, bringing definite properties into existence through interaction, rather than revealing properties that already existed. The universe isn't waiting fully formed for us to discover it. At the quantum level, reality is participatory. The properties we measure come into being through the act of measurement, through the interaction between observer and observed. We're not passive witnesses to an objective reality. We're participants in a universe that becomes definite through interaction. Time speeds up as you age, and there's a mathematical reason why your childhood summers felt endless, while recent years seem to fly by. When you're 10 years old, 1 year represents 10% of your entire lived experience. It's a significant fraction of everything you've known. When you're 50, 1 year is only 2% of your life. The same duration represents a smaller proportion of your total experience, so it feels shorter in comparison to the whole. This proportional theory, proposed by psychologist William James, suggests we perceive time relative to the life we've already lived. Each year is a smaller fraction of your total life as you age, so it seems to pass more quickly. Your 10th year feels long because it's 10% of everything. Your 50th year feels brief because it's only 2%. There's also neurological evidence for changing time, perception. Novel experiences require more processing, more attention, more memory formation. Children encounter novelty constantly. Everything is new, requiring careful attention and encoding. This creates rich, dense memories that make time feel extended. Adults fall into routines, encountering less novelty, processing much of life automatically. This creates sparser memories, making time feel like it passed quickly. The paradox is that when you're experiencing something, time passes slowly if it's novel and engaging. But in memory, periods filled with novel experiences feel longer because they created more memories. Routine periods fly by while living them because automatic processing requires less attention. But they also feel short in retrospect because few memories were formed. If you want to slow time down, seek novelty. Learn new skills, visit new places, meet new people, break routines. Not because this makes time actually pass more slowly, but because it creates the rich memories that, looking back, make a period of life feel substantial rather than fleeting. Time perception is malleable, influenced by attention, novelty, and the density of memory formation. The quantum vacuum isn't empty. It's not a true void, not a region devoid of everything. Instead, it's a roiling sea of virtual particles constantly appearing and disappearing, created from nothing and annihilating back into nothing in timescales too brief to directly observe. This isn't speculation. It's a consequence of quantum field theory and has measurable effects. The Heisenberg uncertainty principle allows energy to spontaneously appear for extremely brief periods, creating particle-antiparticle pairs that exist for a moment before annihilating. The more energy borrowed, the shorter the time it can exist. Virtual particles pop into existence throughout empty space, everywhere, constantly, borrowing energy from the quantum vacuum and repaying it almost instantly. These fluctuations have real, measurable effects. The Casimir effect occurs when two metal plates are placed very close together in vacuum. Virtual particles with wavelengths longer than the gap between plates cannot form in that space, but all wavelengths can form outside. This creates a pressure difference, more virtual particles outside than inside, pushing the plates together. This tiny force has been measured precisely, confirming that quantum vacuum fluctuations are real, physical phenomena. Virtual particles might have driven cosmic inflation, the exponential expansion in the early universe that stretched space from subatomic to cosmic scales in a fraction of a second. They contribute to dark energy, the force driving the universe's accelerating expansion. They affect the precise energy levels of atoms, creating tiny shifts that match theoretical predictions to extraordinary precision. The vacuum, then, is not nothing. It's a quantum field in its lowest energy state. But that state isn't empty. It's seething with activity at scales too small and time scales too brief for us to directly perceive. Empty space is full of potential, full of fleeting particles, full of energy borrowed and repaid in the blink of an eye. The universe doesn't have true emptiness, just different levels of somethingness, different configurations of quantum fields that extend throughout all of reality. Cephalopods, octopuses, squid, cuttlefish can edit their own RNA, allowing them to modify their nervous systems dynamically in ways no other animals can. Most animals, including humans, have genetic information encoded in DNA that gets transcribed into RNA, which then gets translated into proteins. The proteins perform cellular functions. It's a one-way flow. DNA, RNA, protein. Mutations in DNA change the organism permanently, but the RNA faithfully copies whatever DNA says. Cephalopods break this rule. They extensively edit their RNA after transcription, changing the instructions before proteins are made. They use enzymes to modify specific RNA bases, altering the genetic message without changing the underlying DNA. This allows them to produce different proteins from the same genes, fine-tuning their nervous systems in response to current needs. This capability is particularly abundant in neural tissue. Cephalopods can modify genes involved in neural function, adapting their brains and nerves to changing conditions, water temperature, light levels, behavioral demands. They're essentially reprogramming their nervous systems on the fly, tweaking neural proteins to optimize performance for current circumstances. But there's a trade-off. This extensive RNA editing seems to have come at the cost of reduced DNA evolution. Cephalopods evolve more slowly at the DNA level than most other animals. They've sacrificed long-term evolutionary flexibility for short-term adaptive ability, choosing to change themselves within their lifetimes rather than across generations. It's a fundamentally different strategy from the one most life uses, where we change slowly through DNA mutations passed to offspring. Cephalopods change rapidly through RNA editing within their own lifetimes. They're dynamically adaptable in ways we aren't, able to adjust their own biology to immediate circumstances. It's yet another way these alien-seeming creatures are profoundly different from us. Another reminder that intelligence and adaptation can take forms we'd never predict from our own biology. Consciousness remains one of science's greatest mysteries. We can map the brain, trace neural pathways, identify regions involved in perception and decision-making, but we still don't understand how physical matter gives rise to subjective experience. Philosopher David Chalmers calls this the hard problem of consciousness, explaining why there's something it's like to be you. We can explain the easy problems, how the brain processes sensory information, how it stores memories, how it controls behavior. These are complex but approachable through neuroscience. But explaining why these processes feel like something, why there's an inner subjective experience accompanying them, remains profoundly mysterious. When you see the color red, neurons fire in your visual cortex. We can measure this activity, map exactly which cells activate, trace the signal from retina to brain. But why does this neural activity produce the subjective experience of redness? Why isn't it just unconscious information processing? What is it about these particular patterns of neural firing that creates the felt quality of being you, of having experiences? Some scientists think consciousness emerges from information integration. When information is processed in sufficiently complex and interconnected ways, subjective experience emerges. Others think it involves quantum effects in neural microtubules. Still others believe consciousness is fundamental, like mass or charge, a basic property of certain physical systems rather than something that emerges from complexity. We don't have answers. We have theories, hypotheses, frameworks, but no consensus on how matter becomes mind, how objective physical processes generate subjective experience. You are, right now, the most mysterious phenomenon you know. A pattern of matter that somehow knows itself, that experiences reality from within, that has inner life. And despite all our scientific progress, we still can't fully explain how that's possible, how neurons firing create the irreducible fact of your existence as a conscious being. Some physicists propose that the universe might be a hologram, not in the science fiction sense, but in a precise mathematical way that challenges our understanding of reality's fundamental structure. The holographic principle suggests that all the information contained in a three-dimensional region of space can be encoded on its two-dimensional boundary. Like a hologram that appears three-dimensional but stores information in two dimensions, the universe might be a projection from information stored at its edges. This idea emerged from studying black holes. A black hole's entropy, the amount of information it contains, is proportional to its surface area, not its volume. This is strange because we'd expect information content to scale with volume, with the three-dimensional space inside. But for black holes, it's the surface that matters. The information about everything that fell into the black hole is somehow encoded on its event horizon, the two-dimensional surface boundary. Physicist Leonard Susskind and others extended this to suggest that perhaps all of space works this way. Everything we perceive as three-dimensional, our bodies, the Earth, galaxies, might be projections from information encoded on a distant two-dimensional surface. We'd be living in a holographic projection without knowing it, unable to detect the difference between actual three-dimensionality and a sufficiently perfect projection from a lower dimensional surface. This isn't just philosophy. The holographic principle has concrete mathematical formulations, particularly in string theory's ADS-CFT correspondence, which shows precise equivalence between a gravitational theory in curved space and a quantum field theory on its boundary. It's a working tool in theoretical physics, helping solve problems by translating them between equivalent but mathematically simpler formulations. What does it mean if the universe is holographic? Perhaps that spatial dimensions aren't as fundamental as they appear, that reality's deepest description involves fewer dimensions than we perceive, that our three-dimensional experience is emergent from something simpler. Space itself might be an illusion, a convenient way of organizing information that's actually stored elsewhere, in fewer dimensions, in a form we can't directly perceive. Your decisions might be made by your brain before you're consciously aware of deciding, a finding that challenges our intuitions about free will and conscious control. In famous experiments by Benjamin Libet in the 1980s, subjects were asked to flex their wrist whenever they felt like it and report when they first became aware of the urge to move. Electrodes measured both brain activity and the actual movement. The results were unsettling. Brain activity indicating the decision to move began about half a second before subjects reported conscious awareness of deciding. The brain started preparing for movement before the person consciously chose to move. More recent studies using fMRI have pushed this even further. Some research suggests brain activity can predict decisions up to 10 seconds before conscious awareness. Patterns of activity in certain brain regions correlate with which choice a person will make, and these patterns appear well before the person feels they've decided. What does this mean? One interpretation is that consciousness is less in control than we think, that decisions arise from unconscious neural processes, and consciousness is informed of the decision after the fact, creating the illusion of conscious choice. We feel like we're deciding, but the decision has already been made by unconscious processes before awareness catches up. But this interpretation is controversial. Critics note that the early brain activity might represent preparation or bias toward a decision rather than the decision itself, that consciousness might still have the ability to veto unconscious impulses, that the experiments involve trivial decisions made in artificial contexts that might not reflect how we make meaningful choices. The question remains unresolved. Do we have free will in the traditional sense, or is consciousness more of a witness to decisions made by unconscious neural machinery? Are we in control, or does control itself emerge from processes that happen before and beneath awareness? Your sense of agency, of being the author of your actions, might be partly an illusion constructed by your brain, or it might be real in ways these experiments can't capture. We're still figuring it out, still trying to understand the relationship between consciousness and action, between awareness and will. The universe has no center and no edge. Every point can be considered its center, and nowhere is more central than anywhere else. This seems contradictory until you understand what expansion really means. When space expands, it doesn't expand from a center point outward. All points move away from all other points simultaneously. Imagine a loaf of raisin bread rising in the oven. Every raisin moves away from every other raisin, as the dough expands. No raisin is at the center. Each raisin sees all others moving away from it. The expansion isn't happening in space. Space itself is expanding. From Earth, we see distant galaxies receding in all directions. It looks like we're at the center of the expansion, but an observer in any of those distant galaxies would see exactly the same thing. All galaxies receding from them in all directions. Every location appears to be the center because there is no center. The expansion is happening everywhere at once, uniformly, with no privileged position. The Big Bang didn't happen at a point in space that exploded outward. It happened everywhere simultaneously. Every point in the current universe was present at the Big Bang, infinitesimally close to every other point, before space expanded. When we look at the cosmic microwave background, the afterglow of the Big Bang, we're not looking at a distant explosion. We're looking at the light from the hot early universe that has traveled to us from all directions as space expanded. This also means the universe has no edge unless it's finite. And if it's finite, the edge is more like the surface of a sphere. No actual boundary, just curvature that closes back on itself. If you traveled in one direction far enough, you might eventually return to your starting point, having circumnavigated the universe like someone sailing around Earth. The universe is either infinite or unbounded, either extending forever in all directions or curving back on itself. But either way, there's no edge you could reach, no wall marking the end of space, no location that's more central than any other. Every point is equally valid as the center, which means the concept of center doesn't really apply. The universe contains all of space, and space doesn't exist within something larger. Space is all there is. Most of the photons in the universe are ancient relics from the Big Bang, forming the cosmic microwave background radiation that fills all of space. About 400,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this, the universe was ionized plasma, free electrons, scattered photons constantly, making the universe opaque, like being inside a glowing fog. But once atoms formed, photons could travel freely. The universe became transparent, and those first free photons have been traveling ever since. Today, these photons have been stretched by cosmic expansion from visible light to microwaves. They arrive at Earth from all directions, forming a nearly uniform background glow at about 2.7 Kelvin, just a few degrees above absolute zero. This cosmic microwave background is the afterglow of the Big Bang, the oldest light in the universe, a baby picture of the cosmos when it was just 400,000 years old. These photons outnumber all other photons combined. For every photon produced by stars, galaxies, and other sources since the Big Bang, there are about 1 billion cosmic microwave background photons. They fill space uniformly, bathing everything in this ancient radiation. About 1% of the static on an old analog television was caused by these photons. You could literally see the Big Bang in TV static. The cosmic microwave background is remarkably uniform, with temperature variations of only about 1 part in 100,000. But those tiny variations are incredibly important. They're the seeds of all cosmic structure, the density fluctuations that eventually grew into galaxies, clusters, and all the large-scale structure we see today. Every galaxy, every star, every planet traces its origins to slight overdensities visible in this ancient light. Looking at the cosmic microwave background, we're seeing the universe as it was 13.8 billion years ago, observing light that has traveled the entire history of the cosmos to reach us. It's the ultimate time capsule, preserving information about the early universe that we can decode to learn about cosmic history, composition, and evolution. And it's everywhere, always, surrounding us with the light of creation itself. Venus, Earth's hellish twin, might harbor life, not on its scorching surface where temperatures melt lead and atmospheric pressure would crush a submarine, but floating in its clouds. About 50 kilometers up in Venus's atmosphere, conditions are surprisingly Earth-like. The temperature is around 20-30 degrees Celsius, room temperature. The pressure is about 1 atmosphere, the same as sea level on Earth. At this altitude, the crushing heat and pressure of the surface give way to relatively benign conditions. If you could put on just an oxygen mask and acid-resistant suit, you could survive there more easily than on any other world beyond Earth. And here, in these clouds, scientists have detected phosphine, a gas that, on Earth, is only produced by life or industrial processes. The detection is controversial, debated, possibly mistaken. But it's raised the tantalizing possibility that microbes might float in Venus's clouds, drifting through the atmosphere, reproducing in acid droplets, metabolizing sulfur compounds, surviving in an aerial ecosystem unlike anything on Earth. Earth's atmosphere hosts microbes that live their entire lives aloft, never touching ground. Venus's clouds could similarly host a complete airborne biosphere. Organisms might rise and fall in convection currents, dormant spores drifting to higher, colder layers, then falling to warmer regions where they activate and reproduce. It's speculative, but possible. Life adapting to an environment completely different from surface-dwelling organisms, finding habitable niches in places we never expected. Future missions might directly sample Venus's atmosphere, capturing cloud particles and searching for biological signatures. We might find chemistry that can only be explained by metabolism, structures that look like cells, chemical gradients that suggest active life processes. Or we might find that phosphine has some exotic, non-biological source we haven't identified yet. That Venus's clouds are sterile despite their relatively benign conditions. But the possibility remains. Life might exist on Venus, floating through toxic clouds, surviving where no surface environment could support it, reminding us that life's requirements might be more flexible than we think, that habitability isn't limited to surfaces, that the universe might hide biology in places we'd never thought to look. The universe appears fine-tuned for life. The fundamental constants that govern physics, the strength of gravity, the electromagnetic force, the masses of particles, all fall within narrow ranges that allow stars, atoms, and life to exist. Change them even slightly, and the universe becomes lifeless. If gravity were slightly stronger, stars would burn out too quickly for planets to form and life to evolve. Slightly weaker, and stars couldn't form at all. If the strong nuclear force were a bit different, atomic nuclei couldn't hold together, or carbon couldn't form in stars. If electromagnetic force were different, chemistry would be impossible. The constants seem precisely calibrated to allow complexity, life, consciousness. This fine-tuning is real. The ranges are genuinely narrow, often measured in single percentage points. Change many constants by even 1%, and the universe becomes incompatible with any form of complex structure. Is this design? Coincidence? Something else entirely? One explanation is the anthropic principle. We necessarily observe a universe compatible with our existence because we couldn't exist in any other universe. It's selection bias. We don't find ourselves in lifeless universes because we wouldn't exist there to observe them. This explains fine-tuning without requiring design, but it feels unsatisfying, like explaining a coincidence by noting that it had to happen for us to notice it. Another explanation is the multiverse. Perhaps countless universes exist with different constants, and we inhabit one of the rare universes where constants permit life. Most universes are lifeless, but with infinite or near-infinite universes, some must randomly have the right values. Life emerges wherever conditions allow, and observers necessarily find themselves in those rare, hospitable universes. This trades one mystery, fine-tuning, for another, infinite, unobservable universes. We don't know which explanation is correct. Maybe the constants aren't as arbitrary as they seem, connected by deeper physical laws we haven't discovered. Maybe our concept of fine-tuning is naive, assuming only our kind of life is possible when completely different forms of complexity might emerge under different constants. Maybe it is design, though that raises more questions than it answers. The fine-tuning problem remains one of cosmology's deepest puzzles, touching physics, philosophy, and perhaps the ultimate question of why anything exists at all. Quantum superposition means a particle can exist in multiple states simultaneously until observed, literally being in two places at once or spinning in two directions at once. This isn't uncertainty about which state the particle is. It's genuinely being in multiple states simultaneously. Schrödinger's famous cat thought experiment illustrates this. A cat in a box with a quantum trigger for poison is both alive and dead until the box is opened. The quantum system is in superposition of both states, and observation collapses it into one outcome. This seems absurd for cats, and indeed, large objects like cats don't exhibit superposition because they're constantly interacting with their environment, causing continuous measurement that collapses superposition almost instantly. But particles definitely do this. Electrons pass through two slits simultaneously, interfering with themselves. Photons are polarized in multiple directions at once. It's not just theory, it's experimentally verified countless times, the foundation of quantum computing and many quantum technologies. Quantum computers exploit superposition to perform calculations. A classical bit is either 0 or 1. A quantum bit, qubit, is both 0 and 1, simultaneously existing in superposition until measured. Multiple qubits can be in superposition of all possible combinations simultaneously, allowing quantum computers to explore many possible solutions at once, potentially solving certain problems exponentially faster than classical computers. But superposition is fragile. Any interaction with the environment, a stray photon, a vibration, thermal fluctuations, can cause decoherence, collapsing the superposition into a definite state. This is why quantum computers require extreme isolation, near absolute zero temperatures, sophisticated error correction. Maintaining superposition in systems large enough to be useful is extraordinarily difficult. Superposition reveals reality's fundamentally probabilistic nature at quantum scales. Before measurement, particles don't have definite properties. They exist in clouds of probability, being all possibilities simultaneously. Only through measurement, through interaction that forces them to choose, do definite properties emerge. The universe at its deepest level is less certain, less determined, less solid than everyday experience suggests. Time may not be fundamental. It might emerge from more basic, timeless laws of physics, appearing only at macroscopic scales while being absent from reality's deepest description. Some quantum gravity theories, attempting to unify quantum mechanics and general relativity, work better without time as a fundamental parameter. The Wheeler-DeWitt equation, describing the quantum state of the universe, contains no time variable. Time might be emergent, appearing in our experience, but not present in the universe's fundamental description. One proposal suggests time emerges from entropy, the tendency of systems to move toward disorder. We experience time because entropy increases. The past has lower entropy, the future higher entropy, and this gradient creates the arrow of time we perceive. Without entropy's direction, without this asymmetry, there might be no meaningful distinction between past and future. Time might be a consequence of thermodynamics, rather than a fundamental aspect of reality. Another idea connects time to consciousness and quantum mechanics. Perhaps time emerges through the act of observation, through consciousness collapsing quantum superpositions into definite outcomes. The sequence of these collapses creates a timeline, but the collapses themselves might not be occurring in time. Time might be what collapses create rather than what they occur within. This is deeply speculative, pushing at the boundaries of physics where mathematics becomes uncertain and experimental verification impossible. But it addresses real puzzles: the difficulty of merging quantum mechanics with relativity, the mystery of time's arrow, the question of why time flows forward when physical laws are largely time-symmetric. If time isn't fundamental, what does that mean for our experience? We perceive time, live in time, are creatures whose entire existence is temporal. But perhaps this is like temperature. We experience heat and cold, but at the deepest level, there's no such thing as temperature, just molecular motion. Time might similarly be an emergent, macroscopic property that has no counterpart in reality's deepest description, an organizing principle of consciousness rather than a feature of fundamental physics. Matter won over antimatter in the early universe, but it shouldn't have. The Big Bang should have created equal amounts of both, which should have annihilated each other completely, leaving nothing but light. Yet here we are, made of matter, in a universe made of matter. Why? Particle physics says that for every particle, there should be an antimatter counterpart. Electrons have positrons, protons have antiprotons. They're identical except for opposite charge. When created from energy, they appear in equal numbers. Matter and antimatter produced together. So the Big Bang should have created equal amounts, and they should have annihilated upon contact, converting all mass back to energy. The universe should be empty of matter, filled only with light, but there's a tiny asymmetry. For every billion matter-antimatter pairs created, there is one extra matter particle. After all the annihilation, when every antimatter particle found a matter particle to destroy, that 1 in a billion excess of matter remained. That infinitesimal imbalance is everything we see. Every star, every planet, every atom in your body. We exist because of a tiny flaw in the symmetry between matter and antimatter. Why this asymmetry exists is one of physics' greatest mysteries. We've discovered small differences in how matter and antimatter behave, slight asymmetries in particle interactions, violations of CP symmetry, but these known effects aren't large enough to explain the observed matter-antimatter imbalance. Something else must have happened in the early universe, some process we don't fully understand that created slightly more matter than antimatter. This is called baryogenesis, the origin of matter, and it's an active area of research. Perhaps new physics beyond the standard model creates the asymmetry. Perhaps it involves the Higgs field or exotic particle interactions in the first fractions of a second after the Big Bang. Perhaps it's connected to the nature of neutrinos or to conditions in the cosmic inflation era. We don't know. We know there must be an answer because we exist, because the universe contains matter rather than being empty radiation. But the mechanism remains mysterious, a fundamental question about why anything material exists at all. The Drake equation estimates the number of communicating civilizations in our galaxy, but its variables span such enormous ranges that it produces wildly different answers depending on your assumptions. Frank Drake formulated this equation in 1961 to structure thinking about extraterrestrial intelligence. It multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops technology capable of communication, and how long such civilizations survive. Some factors we know reasonably well. Star formation rates are measurable. We've discovered thousands of exoplanets and can estimate how many stars have potentially habitable worlds. But other factors are complete unknowns. How often does life emerge given the right conditions? We have one example, Earth, which tells us almost nothing about probability. Maybe life is inevitable wherever conditions allow, or maybe Earth is extraordinarily lucky and life is vanishingly rare. And even if life is common, how often does it become intelligent? Earth had life for billions of years before intelligence emerged. Maybe intelligence is nearly inevitable given enough time, or maybe it's a singular fluke that happened once in billions of species. We don't know. We can't know with only one example. The final factor, how long civilizations survive, might be the most crucial and most uncertain. Do technological civilizations tend to destroy themselves through war, environmental collapse, or other catastrophes? Or do most survive and persist for millions of years? This factor alone could vary from decades to millions of years, changing the equation's result by many orders of magnitude. Depending on your assumptions, the Drake equation suggests anywhere from we're alone in the galaxy to millions of civilizations exist. Both answers are consistent with the equation and our current knowledge. We might be one of countless civilizations scattered throughout the cosmos, or we might be utterly alone, the only consciousness in billions of stars. Both possibilities are profound, both equally consistent with what we know, and we have no way to determine which is correct without actually finding, or failing to find, evidence of others. Some scientists theorize we might live in a simulation, and there's no way to definitively prove we don't. The simulation hypothesis suggests our reality is a computer program running in some higher reality. The argument goes like this: if civilizations can reach the technological capability to run simulations detailed enough to contain conscious beings, and if they choose to run many such simulations, then there would be far more simulated consciousnesses than biological ones. In a universe with millions of simulations, each containing billions of conscious beings, the probability that any random conscious being is real rather than simulated becomes vanishingly small. This isn't just philosophy. Physicist Nick Bostrom formalized it as a trilemma. Either civilizations never reach the capability to run conscious simulations, or they reach it but choose not to run them, or we are almost certainly living in a simulation. One of these three must be true. If the first two are false, if such simulations are possible and will be created, then simulated realities vastly outnumber base reality, making it overwhelmingly likely we're simulated. Could we detect evidence of simulation? Some suggest looking for computational artifacts, glitches, resolution limits, asymmetries in physical laws that might reflect efficient coding rather than fundamental physics. The finite speed of light could be a frame rate limit. Quantum mechanics pixelation might reflect underlying discrete computation. But none of this is proof. Natural laws could simply happen to look like optimizations without actually being computational shortcuts. Others argue the hypothesis is unfalsifiable and therefore unscientific. If the simulation is perfect, it's indistinguishable from non-simulated reality. Any evidence could be explained away. Any test could be anticipated and accounted for by the simulators. We might be living in a simulation right now, and there might be no way to ever know. It's unsettling partly because it's so uncertain. We can't prove we're not simulated. We can't prove we are. The question might be fundamentally unanswerable, leaving us perpetually uncertain about the ontological status of our own reality, whether we're genuine or simulated, base level or nested within layers of simulation extending upward beyond our ability to detect. The Fermi paradox asks, if intelligent life is likely in the universe, where is everyone? The cosmos is vast and old. If civilizations commonly arise, even spread slowly, they should have colonized the galaxy many times over. Yet we see no signs of anyone. Physicist Enrico Fermi famously asked this during a lunch discussion in 1950. The Milky Way is 13 billion years old and contains hundreds of billions of stars. If even a small fraction host intelligent life, and if even a few of those expand beyond their home worlds, the galaxy should be teeming with civilizations or their artifacts. Yet we detect no signals, no megastructures, no evidence of cosmic engineering, nothing suggesting intelligence beyond Earth. Proposed solutions are numerous and unsettling. Maybe life is far rarer than we think. The Great Filter hypothesis suggests there's some extremely unlikely step between non-life and spacefaring civilization. and we've either passed it or are approaching it. Maybe intelligence usually destroys itself before expanding significantly. Maybe the timescales for communication are wrong. Civilizations might exist but be too short-lived to overlap, like stars blinking on and off, never coexisting long enough to contact each other. Maybe advanced civilizations hide deliberately, practicing cosmic camouflage. Maybe they're here, but we don't recognize them because they're too different, too subtle, too advanced for us to perceive as intelligence. Maybe they transcend physical reality, uploading into simulations or ascending to higher dimensions, leaving no detectable presence. Maybe space travel is fundamentally impractical despite appearing possible. Some physical or economic barrier making expansion beyond home systems impossible. Or maybe we're actually alone. Maybe Earth is unique, unrepeatable, the only place where the billion improbable steps from chemistry to consciousness all occurred. The rare Earth hypothesis suggests planets like ours, with the right star, the right orbit, the right moon-stabilizing axial tilt, the right magnetic field, the right chemistry, might be extraordinarily uncommon. We might live in a galaxy, a universe, where intelligence has emerged exactly once. The silence is profound, the absence of signals, of evidence, of any sign that we're not alone in hundreds of billions of stars. The Fermi paradox forces us to confront either our uniqueness or our mortality. Either we're alone or there's something preventing civilizations from persisting, from expanding, from making themselves known. Both possibilities are sobering. Quantum entanglement suggests the universe may be fundamentally non-local, that everything remains connected in ways that transcend space, that separateness might be an illusion at reality's deepest level. When particles become entangled, their quantum states become correlated in ways that persist across any distance. Measure one particle, and you instantly know something about its partner, even if they're light years apart. The correlation exists without any signal passing between them, without anything traveling through space to connect them. They remain linked by something that doesn't respect spatial separation. Einstein found this deeply troubling. It seemed to violate locality, the principle that objects are influenced only by their immediate surroundings, that effects propagate through space at limited speeds. Entanglement appeared to allow instantaneous correlations across any distance, suggesting spooky action at a distance, as Einstein called it, phenomena that defied our understanding of how separated things can be related. But experiments have confirmed it's real. Bell's theorem and subsequent tests have shown that quantum mechanics predictions about entanglement are correct, and they can't be explained by local hidden variables, by particles carrying information about their correlated properties from the moment of entanglement. The correlations are genuinely non-local, arising only at measurement, yet perfectly coordinated across space. What does this mean philosophically? Perhaps that reality is fundamentally interconnected, that the appearance of separate, independent objects is a macroscopic illusion, that at the quantum level everything remains entangled with everything it's ever interacted with, creating a web of correlations spanning the universe. Separateness might be approximate, emergent, a useful fiction at large scales, but not fundamental. You've interacted with countless particles throughout your life. Those particles are now scattered, some part of other objects, some drifted away, but the entanglements remain, connecting you through invisible quantum correlations to everything you've ever touched, every breath you've taken, every photon that's bounced off your skin. At the quantum level, perhaps nothing is truly separate. Perhaps we're all part of a unified quantum state that only appears divided into distinct objects from our macroscopic perspective. The heat death of the universe, when all energy is evenly distributed and no work can be performed, may be inevitable in the far future, the ultimate fate awaiting reality after unimaginable spans of time. Entropy increases. This is thermodynamics' second law, one of the most reliable principles in physics. Ordered energy, concentrated in stars, in chemical bonds, in organized structures, gradually disperses, spreads out, becomes uniform. Stars burn out. Black holes evaporate. Even protons might decay given enough time. Eventually, in perhaps 100 years or longer, the universe reaches maximum entropy. At that point, everything is the same temperature, just slightly above absolute zero, a thin soup of photons and elementary particles spread across expanding space. No temperature gradients exist to drive engines. No concentrations of energy remain to power processes. No stars shine. No planets orbit. No chemistry occurs. Time becomes meaningless because nothing changes. The universe reaches a state of complete equilibrium, eternal and static. This is heat death, not an explosion or collapse, but a gradual fading into darkness and uniformity. The universe doesn't end so much as it stops, settling into a final configuration where nothing can happen because there's no energy difference anywhere to drive events. Existence continues but becomes a frozen wasteland, devoid of complexity, structure, life, or change. It's trillions upon trillions of years away, incomprehensibly distant even compared to the universe's current age. But thermodynamics suggests it's unavoidable unless the laws of physics are different than we think. Every star that burns hastens it slightly. Every process that releases heat moves the universe incrementally toward this ultimate equilibrium. Yet there's something almost peaceful about it. After all the drama, stars forming and dying, galaxies colliding, black holes consuming matter, the universe settles into stillness. It's the longest of endings, a gradual dimming rather than sudden cessation, reality gently fading into a darkness that will last forever. Everything that rises must fall, everything that burns must cool, everything that's organized must eventually dissolve. And in the end, after time beyond imagining, the cosmos rests. We don't know if mathematics is discovered or invented, whether it exists independently of minds or is a human creation. This might sound like pointless philosophy, but it touches something deep about reality's nature. Mathematics describes reality with uncanny precision. The equations of physics predict phenomena perfectly, from planetary orbits to quantum behavior. Math seems to capture truths about the universe, truths that exist whether anyone knows them or not. The Pythagorean theorem was true before Pythagoras, applies on distant planets where no mathematician has ever lived, would remain true if all conscious beings disappeared. This suggests mathematics exists independently, that we discover its truths rather than inventing them. But mathematics is also a human activity. We create axioms, definitions, proof methods. Different mathematical systems are possible: Euclidean and non-Euclidean geometries, various set theories, alternative logical frameworks. Which mathematics we use seems like a choice, a creative act. And mathematical objects, numbers, sets, functions, don't exist physically. You can't find the number 5 anywhere in nature, only 5 of various things. Mathematics seems like a mental construct, a language we invented to describe patterns. Perhaps the answer is both. We invent mathematical frameworks and languages, but we discover truths within those frameworks. We create chess rules, but we discover which strategies win. Similarly, we might create mathematical systems, but we discover what's true within them, and those truths exist independently of whether we've found them yet. Or perhaps math is an emergent property of any consciousness complex enough to abstract patterns, as inevitable as physics, but requiring minds to exist. Different alien civilizations would develop mathematics, possibly with different notation and emphasis, but converging on the same underlying truths because they're describing the same reality. The question matters because it affects how we think about scientific knowledge. Are we uncovering a pre-existing mathematical structure underlying reality, reading the universe's own language? Or are we constructing models that happen to work, useful fictions that predict observations without necessarily revealing fundamental truth? The answer shapes our understanding of what science is actually doing: discovering or constructing, revealing or modeling. The most probable state of any system is equilibrium, uniformity, maximum entropy. Yet life exists by being persistently out of equilibrium, by fighting entropy, by maintaining improbable order against the universe's tendency toward disorder. Every cell in your body is extraordinarily organized. Membranes maintaining concentration gradients, proteins folded into precise shapes, DNA encoding information that would degrade if not actively maintained. This organization requires constant energy input. You eat to extract chemical energy, which powers cellular processes that maintain order, repair damage, resist decay. Stop eating and entropy wins. Organization breaks down, structure dissolves. Life is fundamentally anti-entropic, locally decreasing entropy within organisms while increasing it in the environment. You're highly ordered, but you generate heat and waste products that increase total entropy. You're temporarily fighting the universe's tendency toward disorder, maintaining your improbable complexity by consuming energy and exporting entropy to your surroundings. This can't last forever. Individuals die, complexity unravels, organization returns to chaos. But life as a process persists by reproduction, passing organizational patterns to new individuals, maintaining the fight against entropy across generations. Life is a pattern that persists by constantly being rebuilt, like a whirlpool that maintains its form even as water flows through it, or a flame that stays the same shape while consuming different fuel. Ultimately, though, entropy will win. In the heat death of the universe, when all energy is evenly distributed, life becomes impossible. No gradients exist to extract energy from. No work can be performed. The fight against entropy that defines life ends not with defeat, but with the absence of any battleground. No energy differences remain to exploit. no way to maintain organization against equilibrium. So life is precious precisely because it's temporary and improbable. We're patterns of order in a universe trending toward disorder, maintaining ourselves through constant effort, existing only because we're far from equilibrium and willing to work to stay there. Every breath, every heartbeat, every thought is an act of resistance against entropy, a temporary victory in a battle that ultimately cannot be won, but can be fought courageously for however long energy allows. Every point in space may contain a universe. Some theories suggest reality branches infinitely, creating parallel worlds that diverge with each quantum event, dimensions beyond our perception, possibilities we cannot access. The many worlds interpretation of quantum mechanics proposes that every quantum measurement causes the universe to split. When a particle in superposition is measured, both outcomes occur, but in separate branches of reality. You observe one outcome, another version of you in a parallel universe observes the other. Both branches are equally real. Both continue evolving. Both contain versions of you experiencing different results. If true, there are countless near-identical universes where everything is the same, except for tiny quantum differences, and countless more where different chains of quantum events led to radically different outcomes. Universes where you made different choices, where history went differently, where improbable events happened or didn't. Every possibility permitted by quantum mechanics is realized somewhere in the vast branching structure of parallel realities. String theory suggests additional spatial dimensions, perhaps 7 extra dimensions beyond the 3 we perceive, curled up too small to detect, or perhaps entire parallel brains, floating in higher dimensional space, whole universes separated from ours by distances measured not in meters, but in extra dimensions, perpendicular to all directions we can point. These aren't detectable. Parallel worlds don't interact with ours. That's what makes them parallel. Extra dimensions either are too small to access or exist outside our dimensional subspace. They're theoretical constructs that solve mathematical problems in physics, make equations work, explain observations, but might never be directly observable. Yet if true, they mean our universe, everything we can see, measure, experience, is just a tiny slice of reality. We'd be living in one branch of an infinite tree, one 3-dimensional slice through a higher dimensional space, unable to perceive the vast majority of what exists. Reality would be incomprehensibly larger, richer, more complex than the universe we inhabit, most of it forever beyond our reach, existing parallel to our experience but inaccessible, invisible, undetectable except through mathematical inference. Science shows us that we're simultaneously insignificant and precious. We're just one species on one planet orbiting one star among hundreds of billions, in one galaxy among hundreds of billions. Yet we're the only known place where the universe has become aware of itself. Cosmically, we're nothing. Earth is a pale blue dot, barely visible from the outer solar system, invisible beyond. The Voyager 1 photograph taken from billions of miles away shows us as a single pixel, a speck of dust suspended in a sunbeam. Everything that's ever happened, all of human history, every empire and war, every love and loss, occurred on this mote suspended in cosmic darkness. We're made of common elements, following ordinary physics, subject to the same forces, governing every other particle. We're temporary configurations of matter that arose through natural processes, will exist briefly, then dissolve. Nothing about us is cosmically special. We're not central, not unique in principle, not necessary for the universe to function. The cosmos doesn't need us and wouldn't notice our absence. And yet, we're patterns of matter that think, that wonder, that ask questions about existence. We're the way the universe reflects on itself, experiences itself, tries to understand itself. Through us, the cosmos has developed consciousness, achieved self-awareness, begun the project of comprehending its own nature. We're how matter knows it exists, how physics contemplates physics, how the universe observes itself from within. This makes us precious despite our insignificance, or perhaps because of it. We're improbable, lucky, remarkable, not for being central, but for existing at all. We're conscious witnesses to reality in a cosmos that seems largely indifferent to consciousness. And we're alone as far as we know, the only minds in a universe of immense scale and age, singular in our awareness, despite our cosmic smallness. Perhaps that's enough. To be temporary patterns that nevertheless experience beauty, understand mathematics, love others, contemplate the stars. To be matter organized in ways that permit wonder, gratitude, curiosity. To be finite beings asking infinite questions, knowing we're small, yet daring to understand the whole. We're made of stardust, contemplating stars, the universe experiencing itself temporarily before returning to unconscious matter. And in that brief moment of awareness, we find meaning, create purpose, make existence conscious, even knowing it won't last. The universe is under no obligation to make sense to us. Reality doesn't owe us comprehensibility, doesn't have to operate according to our intuitions, isn't required to be ultimately knowable. Yet we continue searching for understanding anyway, perhaps because searching is what conscious beings do. We've made remarkable progress. We understand atoms and galaxies, evolution and relativity, quantum mechanics and molecular biology. We've learned the universe's age, composition, history. We've split atoms, decoded DNA, photographed black holes. We've extended our comprehension from immediate experience to cosmic scales, from seconds to billions of years, from macroscopic to quantum. But mysteries remain. Consciousness, dark matter and dark energy, quantum gravity, the origin of the universe, why anything exists at all. Some questions might have answers we'll eventually find. Others might be fundamentally beyond our capacity, either because reality doesn't work in ways our minds can grasp, or because certain truths are inaccessible from within the universe, requiring external perspective we can never achieve. We might be like fish trying to understand flight, or two-dimensional beings trying to grasp three-dimensional space. Our brains evolved to navigate social groups and physical environments, not to comprehend quantum fields or higher dimensions. That we can understand as much as we do is perhaps remarkable, suggesting either that the universe is surprisingly comprehensible or that we're surprisingly capable, probably both. Perhaps the most profound fact is that we try, despite uncertainty, despite mystery, despite the possibility that some truths are forever beyond reach. We continue asking questions, seeking patterns, constructing theories, testing ideas. We're driven by curiosity, even knowing curiosity might never be fully satisfied, compelled to understand even if complete understanding is impossible. And maybe that's the point. Not to reach final answers, perhaps there are none, or perhaps they're inaccessible, but to engage in the search itself. To be conscious beings wondering about consciousness, finite minds contemplating infinity, temporary patterns trying to understand the permanent laws governing their own existence. The questions might matter more than answers, the journey more than any destination. So as you drift towards sleep, as consciousness fades and the questions quiet, perhaps take comfort in this. You're part of the universe asking questions about itself. You're matter that thinks, stardust that wonders, a brief configuration of atoms that nevertheless seeks understanding, and that seeking, that wonder, that curiosity persisting despite mystery, perhaps that's what makes existence meaningful. Not the answers we find, but the fact that we dare to look, continue asking, keep searching even knowing we might never find everything we seek. The universe doesn't guarantee comprehensibility, but here we are anyway, minds in cosmos, consciousness arising from matter, asking why and how and what it all means. And in that asking, in that persistent curiosity, we find something precious, the joy of wondering, the beauty of mystery, the profound privilege of being aware in an ancient cosmos still full of secrets waiting patiently for whoever might be curious enough to look. And with that, we've reached the end of our journey through 100 scientific facts, 100 glimpses into the strangeness and beauty of reality, from the smallest particles to the largest structures, from the beginning of time to its possible end. Some of these facts might stay with you. Others might fade as sleep takes hold, slipping away like dreams upon waking. That's perfectly fine. The point wasn't to memorize, wasn't to test or challenge, but simply to wander together through the landscape of knowledge, to let curiosity be a gentle companion as consciousness fades. Science is many things, a method, a body of knowledge, a way of asking questions, but perhaps most fundamentally, it's a form of wonder, a systematic way of being amazed by reality, of taking nothing for granted, of looking closely at the universe and finding it stranger, more intricate, more beautiful than we imagined. Tonight, we've practiced that wonder together, letting it carry us through facts, both comforting and unsettling, both familiar and alien. You are made of stardust. You are patterns of matter contemplating matter. You exist improbably in a vast cosmos that somehow permitted your existence. And for a brief time, your lifetime, humanity's time, perhaps consciousness's time in the universe, you get to observe, to wonder, to understand. That's extraordinary. That's precious. That's enough. Sleep well. Let these thoughts drift where they will. Tomorrow brings new questions, new wonders, new opportunities to be amazed by the universe we briefly inhabit. But for now, rest. Let consciousness fade. You've earned it, and the cosmos will still be here, still mysterious, still beautiful when you wake. Good night.